In the vast silence that stretches above us, a hidden truth quietly waits to be uncovered. What if the emptiness we have come to associate with space is not as empty as we think? Imagine for a moment a universe draped not in nothingness, but in an invisible substance, permeating every inch between the stars, planets, and galaxies. What if space itself was filled with something that our current understanding has yet to fully grasp? Such a revelation would shift everything. The cosmos we've come to know would no longer appear as a vast, silent expanse, but would transform into a place both alien and familiar, where the boundaries of our reality would be redefined. The textbooks of science would become obsolete, replaced by an entirely new understanding of the universe. Spacecraft would no longer coast effortlessly across the cosmic void, as though floating through nothingness. Instead, they would find themselves crawling through what might feel like cosmic molasses, dragging through a thick medium that could affect every journey and every discovery. Even the night sky, once filled only with the pinpricks of distant stars, would begin to hum with sound, vibrating through this invisible, all-encompassing medium. The vacuum of space, long thought to be a defining feature of the cosmos, holds a paradox. It is the reason the footprints of Apollo astronauts remain sharp and clear on the surface of the moon, unmarred by wind or rain. It's the reason spacecraft like Voyager have been able to travel for billions of miles with seemingly no need for fuel. But what if space wasn't empty? What if it contained some form of matter, something that would fundamentally alter our understanding of the universe and the very fabric of reality? In the past century, our perception of space has undergone a dramatic evolution. Gone is the notion of an empty void, replaced by a view of the universe as a vast, expanding fabric, what scientists now call space-time. This four-dimensional construct, central to Einstein's theory of relativity, is not just a backdrop for stars and galaxies, it is the very medium in which they exist and interact. Massive objects like planets and stars warp this fabric, influencing everything from the path of light to the very flow of time itself. This realization has given rise to an entirely new understanding of how the universe works, where time and space are not isolated phenomena, but are intrinsically linked. More recently, the discovery of dark energy, a mysterious force accelerating the expansion of the universe, has shaken the scientific community, suggesting that the universe might continue to expand indefinitely, defying any expectation that it might one day collapse upon itself. While we traditionally think of a vacuum as a space completely devoid of matter, even the most expansive voids of space defy this notion. Achieving a perfect vacuum, a space entirely free of particles, remains an impossibility, even in the depths of the cosmos. In truth, space is never truly empty. What we consider a vacuum is merely a region with an extremely low particle density, a place where particles are spread out so thinly that for all practical purposes, it seems empty. On Earth, we can artificially create vacuums using specialized equipment, measuring how close we come to true emptiness. The quality of these vacuums is often described by their pressure. The lower the pressure, the closer we are to a true vacuum. However, even in these conditions, the vacuum is not completely devoid of activity. At the quantum level, even a vacuum is brimming with fluctuating electromagnetic fields and virtual particles that spontaneously materialize and vanish in an ongoing dance. These quantum fluctuations can give rise to phenomena such as the Casimir effect, where two uncharged plates placed in a vacuum experience a subtle yet measurable attractive force, a force born from the very emptiness itself. These subtle forces and phenomena remind us that the so-called emptiness of space is far from still. In fact, space is teeming with invisible energy and fluctuating particles, constantly shifting and interacting in ways that challenge our most basic assumptions about the nature of nothingness. In scientific and technological applications, understanding vacuums has proven crucial. From particle accelerators to the packaging of food, the principles of vacuum science play an essential role. But in space exploration, the vacuum of space presents both challenges and opportunities for spacecraft design. One of the most defining features of space is its extreme emptiness. Between the stars of our galaxy, a single cubic meter contains only a few atoms. And in the vast voids between galaxies, the particle density drops to an almost negligible level, fewer than one atom per cubic meter. To put this in perspective, the air we breathe contains around 1 sextillion molecules per cubic meter, one followed by 21 zeros. In comparison, the vacuum of space is astonishingly devoid of matter. However, this emptiness is not complete. Space does contain trace amounts of hydrogen and helium, the two most abundant elements in the universe, along with the occasional wisps of other elements. These sparse atoms form tenuous clouds that can stretch across vast stretches of the cosmos, forming the faintest trace of matter in the otherwise empty expanse. In addition to these sparse clouds of gas, space is also filled with electromagnetic radiation. The most pervasive of this is the cosmic microwave background, the faint afterglow of the Big Bang, which permeates the universe and provides a glimpse into the earliest moments of the cosmos. While the expanse between galaxies may seem devoid of activity, it is far from silent or inactive. On the quantum scale, space is alive with constant motion. Virtual particles appear and disappear, while dark energy, an unseen and largely unexplained force, permeates the cosmos, driving the ever-accelerating expansion of the universe. This dark energy, along with the invisible mass of dark matter, makes up most of the universe's content, reminding us that even in what seems like emptiness, there is far more than meets the eye. Intergalactic space, the vast and seemingly barren regions between galaxies, is one of the most extreme examples of emptiness in the universe. Here, the average density of matter is astonishingly low. The voids between galaxies are so sparse that, on average, they contain only 1 atom per cubic meter. This density is trillions of times less than the air we breathe. And if we were to take a volume of intergalactic space equal to the volume of the Earth, it would contain less mass than a single grain of sand. Despite this extreme emptiness, these vast regions still contain significant amounts of ordinary matter, mostly in the form of hydrogen and helium, though scattered so sparsely that they are nearly impossible to detect with current technology. These empty expanses of space may seem devoid of activity, but they are crucial to the structure and evolution of the universe. Cosmic rays, high-energy particles traveling through the void, sweep across these vast stretches of space, while occasional stars are ejected from their home galaxies by powerful gravitational interactions. The study of these seemingly empty regions helps us understand the universe on the largest scales, providing insight into its formation and eventual fate. While the vacuum of space may seem like a quiet, empty backdrop to the grand drama of the cosmos, it is in fact far more extreme than any vacuum we could ever create on Earth. The vacuum of intergalactic space is so empty that it surpasses the capabilities of even our most advanced technology. On Earth, we can create vacuums with a particle density of about 100,000 molecules per cubic centimeter. While this might seem impressively empty, it is still many orders of magnitude denser than the voids of space. If we could somehow bring a cubic meter of intergalactic space to Earth, it would contain fewer particles than the number of grains of sand found on all the beaches of our planet. This astonishing emptiness allows light and other forms of electromagnetic radiation to travel uninterrupted across vast distances, and it ensures that any matter, whether a tiny speck of dust or a massive star, experiences almost no friction as it moves through the cosmos. The near total absence of matter means that the universe in many ways is both more empty and more full than we ever imagined. However, it is crucial to recognize that space is far from uniformly empty, especially in the vicinity of planets and stars. The interstellar medium, the seemingly void regions between stars, is not truly devoid of matter. In fact, these regions contain a much denser concentration of particles than the vast emptiness between galaxies. Primarily composed of hydrogen atoms, this thin soup is far denser than the intergalactic medium, but still incredibly sparse when compared to the dense matter we encounter on Earth. Despite appearing empty, space near celestial bodies is far from devoid of substance. It is teeming with particles, each interacting in complex and often unseen ways. Virtual particles, though invisible and ephemeral, are another fascinating phenomenon that exists within the vacuum of space. These quantum entities seem to emerge out of nowhere, only to vanish almost immediately, popping in and out of existence as if following an unpredictable cosmic dance. They arise due to the random fluctuations in the quantum field, a direct result of the uncertainty principle, a fundamental idea in quantum mechanics. Unlike regular particles, which are stable and measurable, virtual particles are incredibly short-lived, existing only for fractions of a second, far too brief to be directly observed. This unpredictable behavior challenges our traditional notions of a void and reveals that even in the empty stretches of space, there is a vibrant, dynamic field of activity. The vacuum of space, contrary to our expectations of nothingness, is far from empty. It is filled with potential energy, with fluctuating fields that give birth to these transient particles. The continuous creation and annihilation of these virtual particles is not just a theoretical abstraction. It is a crucial part of the fabric of the universe. The phenomenon even manifests in observable effects, such as the Casimir effect, where two uncharged plates placed in a vacuum experience a minuscule yet measurable attractive force due to the constant activity of virtual particles. This subtle but persistent dance of virtual particles plays a significant role in many areas of physics, contributing to the forces that govern particle interactions, altering the energy of the vacuum, and influencing the behavior of the cosmos in ways that were once difficult to understand. It suggests that space, in its apparent emptiness, is not a stagnant void, but an active, seething realm of fluctuating quantum fields. This concept of virtual particles reshapes our understanding of the universe, reminding us that even in the quietest corners of space, there is always something happening at a level far beyond our perception. In a similar vein, quantum foam is a profound concept that takes us deeper into the very structure of space and time. At incredibly small scales, far smaller than atoms, the universe ceases to appear smooth and uniform. Instead, it behaves like a roiling, turbulent sea, with constant fluctuations occurring at the quantum level. This chaotic dance of particles leads to the formation of a foam structure within space itself. These fluctuations cause particles to emerge and disappear in an almost perpetual cycle, creating a subatomic texture that cannot be ignored. Quantum foam challenges our traditional views of space as a serene and featureless void. Instead, it suggests that at the most fundamental level, space has a granular texture, and there is no true emptiness, even in the most seemingly desolate regions of the universe. The idea that space itself has such a grainy texture opens up new avenues of inquiry for scientists, particularly those attempting to reconcile quantum mechanics with the theory of gravity. Some theorists even speculate that this very foam-like structure might be tied to the mysterious phenomenon of dark energy, which is driving the accelerated expansion of the universe. The implications of this theory are profound, suggesting that the very nature of space might hold the key to unlocking some of the most elusive mysteries of the cosmos, including the behavior of black holes and the origins of the universe itself. In studying quantum foam, scientists are inching closer to a deeper understanding of space, pushing the boundaries of our knowledge about the nature of reality itself. Looking back through history, ancient civilizations had their own interpretations of the cosmos, blending observation, mythology, and religious beliefs. For many early cultures, the night sky was not just a canvas of distant stars, but a sacred, celestial dome that framed their worldview. In Egypt, the goddess Nut was envisioned as arching over the earth, her body adorned with stars representing the heavens themselves. Greek astronomers, particularly those like Ptolemy, attempted to understand the movements of celestial bodies by developing intricate models of spheres that supposedly encase the planets and stars. In Mesopotamia, the Babylonians recorded the positions of stars and planets with remarkable precision, believing the heavens were the domain of gods and divine forces, with each celestial body symbolizing a god or a powerful entity. Similarly, Chinese astronomers charted the night sky, dividing it into constellations that not only helped guide their understanding of the stars, but also played a central role in timekeeping and predicting seasonal events. Native American cultures saw the constellations as a means of storytelling, connecting their ancestors to the stars and finding guidance in their celestial patterns. The Mayans, with their advanced calendars, viewed the movements of the stars not just as a scientific pursuit, but as an integral part of their society, linking the heavens to their agricultural cycles and religious practices. Though these ancient interpretations of space were often far from the scientific understanding we possess today, they laid the foundation for the development of modern astronomy. They demonstrate humanity's intrinsic curiosity about the universe and our unceasing desire to understand the forces that govern our existence. The journey from mythological and religious conceptions of the stars to the modern science of astronomy is one of humanity's most significant intellectual achievements, illustrating our continuous quest to comprehend our place in the vast, ever-expanding cosmos. The early scientific understanding of space was starkly different from the knowledge we now hold. Ancient Greek philosophers, for instance, proposed the idea of celestial spheres, believing that the planets and stars were encased in perfect, transparent spheres that revolved around the Earth. This geocentric model, which placed Earth at the center of the universe, persisted for centuries. It was only in the 16th and 17th centuries, as astronomers such as Copernicus and Galileo questioned the geocentric view, that the nature of space began to be reconsidered. As telescopes improved and observations became more precise, the idea of an Earth-centered universe was slowly replaced by a heliocentric model, placing the Sun at the center of our solar system. At the same time, scientists began to contemplate the nature of the space that lay between the celestial bodies. René Descartes, for instance, postulated the existence of an invisible substance called ether, which he believed was necessary for the transmission of light and the movement of the planets. This idea of ether, a medium that filled the universe and allowed light to travel, gained widespread acceptance and remained influential for centuries. Isaac Newton, though he fundamentally revolutionized our understanding of gravity and motion, still grappled with the concept of empty space. He proposed the idea of absolute space, a fixed, immovable framework in which all objects existed and moved, and even entertained the possibility of a luminiferous ether through which light could travel. Despite the elegance of the ether theory, it was eventually challenged by new discoveries and the advent of new experimental techniques. As the 19th century drew to a close, scientists like James Clerk Maxwell began incorporating the idea of ether into their explanations of electromagnetic phenomena, only to later find that the concept of a vacuum, an empty, formless space, was far more accurate. It was not until the early 20th century, with the publication of Albert Einstein's theories of relativity, that a new understanding of space began to take shape. In relativity, space was no longer an empty void, but a dynamic, flexible entity that could bend and stretch in response to mass and energy. This new understanding of space laid the groundwork for modern physics and our understanding of the universe. The concept of space as a vacuum, as an almost perfect void, was initially proposed by Evangelista Torricelli in the 17th century, when he conducted experiments with mercury barometers to demonstrate the existence of a vacuum above the mercury column. These experiments, which showed that air could be removed from a space, were some of the first to provide experimental evidence for the concept of a vacuum. Further advancements in vacuum technology, such as Otto von Guericke's creation of the first vacuum pump, deepened our understanding of space. His public demonstrations, particularly the famous Magdeburg Hemispheres experiment, showed how the force of atmospheric pressure could prevent two metal hemispheres from being pulled apart when the air between them was evacuated. These early experiments helped establish the notion of a vacuum, though it was only with the development of rocket technology and the exploration of space in the 20th century that scientists were able to directly study the nature of space beyond Earth's atmosphere. Today, we know that while space is not a perfect vacuum, it is remarkably empty compared to the dense environments we experience on Earth. The regions between stars and galaxies, which make up the vast majority of the universe, contain only a few atoms per cubic meter. In these almost perfect vacuums, the particles that do exist are spread out so thinly that the space between stars is one of the emptiest environments known to science. Despite this emptiness, the vacuum of space continues to play a fundamental role in the workings of the universe, providing the backdrop against which the cosmic drama unfolds. However, as scientific experiments grew more intricate and precise, the elusive idea of the ether continued to evade detection. This led to a pivotal turning point in the late 19th century. In 1887, the groundbreaking Michelson-Morley experiment cast doubt on the very foundation of the ether theory, marking a dramatic shift in our understanding of the universe. This experiment sought to detect the presence of the ether, a substance believed to fill all of space and provide a medium through which light waves could propagate. For centuries, scientists had speculated that the ether was a stationary, invisible substance through which the Earth moved, like a boat cutting through water. But when Albert Michelson and Edward Morley designed a clever apparatus to test this hypothesis, their results were completely unexpected. The experiment was built around an interferometer, an intricate device capable of measuring the subtle changes in the speed of light. If the Earth was indeed moving through the ether, Michelson and Morley hypothesized that light traveling in the direction of Earth's motion would experience a slight slowdown, while light traveling at a right angle to this motion would travel at a different speed. It was a simple yet powerful test. If the ether existed, they would detect its effects by observing a change in the speed of light depending on its direction. But much to their astonishment, the experiment revealed no difference at all. Light traveled at the same speed, regardless of direction. The null result, as it came to be known, dealt a severe blow to the ether theory and opened the door to an entirely new way of thinking about space and time. The implications were far-reaching, leading to the eventual abandonment of the ether concept. In the years that followed, the Michelson-Morley experiment was repeated multiple times, with each iteration only confirming the original result. No evidence of the ether ever emerged. The failure to detect the ether did not, however, end the search for understanding. It instead set the stage for a radical new theory that would reshape the very fabric of reality. That theory came from Albert Einstein, whose special theory of relativity, published in 1905, completely abandoned the notion of a medium like the ether, and instead proposed that space itself was a dynamic entity. According to Einstein, space was not an empty vacuum, but one with its own intrinsic properties. Space, in his view, could bend, stretch, and warp in response to the presence of matter and energy. The most decisive blow to the ether concept came in 1932, when Roy Kennedy and Edward Thorndike conducted their own experiment to further investigate the idea. They, too, failed to find any trace of the ether, reinforcing the conclusions drawn from earlier experiments. The elegance and simplicity of Einstein's special relativity were quickly accepted by the scientific community, and with time, the ether theory was left behind. Einstein's work did far more than just dismiss the ether. It changed the way humanity understood the universe. Before Einstein, the prevailing view of space was that it was a static, immutable backdrop against which all events occurred. The universe unfolded on this fixed stage, and time passed uniformly for all observers. But Einstein's special theory of relativity revolutionized this perspective. He showed that space and time were not separate entities, but part of a unified whole, what he called space-time. Events in the universe, it turned out, were far more interconnected and flexible than anyone had imagined. Time was no longer a constant, universal tick. It could dilate and contract depending on an observer's motion. Similarly, distances could stretch or shrink based on relative speeds. In other words, the passage of time and the measurement of distance were not absolute, but depended on the frame of reference of the observer. In the years that followed, Einstein's work continued to astonish and enlighten. His general theory of relativity, published in 1915, expanded on his earlier ideas. It showed that spacetime was not simply a passive arena in which events played out. It could be warped and curved by the presence of mass and energy. The analogy Einstein used was simple, yet profound. Imagine a stretched rubber sheet with a heavy ball placed on it. The ball would cause the sheet to curve around it, and any smaller objects placed on the sheet would be drawn toward the ball. Similarly, massive objects like stars and planets warp spacetime, that creating what we experience as gravity. Rather than being a mysterious force transmitted across empty space, gravity became an effect of the curvature of spacetime itself. This idea led to a complete reimagining of the cosmos. Suddenly, the universe was not a static, unchanging void. It was a dynamic, fluid expanse in which space could stretch, contract, and ripple with gravitational waves. Einstein's theories became the cornerstone of modern cosmology, laying the groundwork for our understanding of black holes, the expansion of the universe, and the very nature of time and space. But Einstein's theories were not the final word in our understanding of space. In the early 20th century, quantum mechanics emerged as another game changer. Quantum mechanics revealed that space, at its most fundamental level, is far from empty. Instead, it is teeming with activity, constantly bubbling with virtual particles that pop in and out of existence. This concept, often referred to as quantum foam, suggested that space itself is filled with an inherent uncertainty, a kind of frothing sea of energy that gives rise to fluctuations in the fabric of reality. At the quantum level, space was no longer a passive void, but an active, dynamic participant in the unfolding of events. This was a far cry from the classical idea of space as an empty stage for the drama of the universe to play out. Furthermore, quantum mechanics introduced the idea of quantum fields, omnipresent fields that permeate all of space. Different particles arise as excitations of these fields, much like waves on the surface of the ocean. In this framework, space and matter were no longer separate. They were intricately connected. The quantum world also revealed strange phenomena like quantum entanglement, where particles could instantaneously influence each other over vast distances. This spooky action at a distance, as Einstein famously called it, challenged our classical notions of locality and suggested that space itself might not be as fundamental or as absolute as we once thought. But what if space were suddenly to cease being a vacuum, filled with nothing but the void between stars? What would happen to the universe? The consequences would be immediate, catastrophic, and far-reaching. The empty stretches of space between celestial bodies would no longer be empty. Instead, they would suddenly fill with matter, altering the fundamental nature of the universe in dramatic ways. Gravity, which holds planets and stars in their orbits, would be thrown into chaos. The delicate balance of our solar system could be disrupted, potentially sending Earth careening away from its life-sustaining orbit around the Sun. Moreover, the sudden appearance of matter in space would profoundly impact the propagation of light and other forms of electromagnetic radiation. Stars, long the beacons of the night sky, would no longer be visible. Their light would be scattered or absorbed by the newly introduced matter, plunging Earth into darkness. The effects would extend even to the most basic processes of life. Photosynthesis, which depends on sunlight, could grind to a halt, triggering a cascade of disastrous consequences for life on Earth. The introduction of matter into space would also generate friction. Planets, moons, and asteroids would all experience resistance as they moved through this newly populated cosmos. Over time, this friction would slow down celestial bodies, potentially causing entire solar systems to collapse. The universe we know and understand would cease to exist. Instead, a dense, chaotic environment would emerge, hostile to the formation and survival of galaxies, stars, and planets. In such a scenario, our entire understanding of the universe would be called into question. Physics itself would need to be rewritten. The concept of a vacuum, space as an empty void, would no longer hold. Instead, space would be filled with a substance, a medium that permeates everything. This substance would behave in strange and unpredictable ways, challenging our most basic ideas of motion, light, and gravity. Objects moving through this space-filling substance would experience resistance, much like a boat moving through water. This would fundamentally alter our laws of motion and force us to rethink our entire understanding of the physical universe. Electromagnetic waves, including light, would behave differently in this substance-filled space. Their speed and propagation might change, altering our understanding of the cosmic speed limit. The very nature of light might shift, as this hypothetical substance could scatter or absorb radiation in ways we have not yet imagined. Gravity, too, would likely function differently. The presence of this substance could influence how gravity propagates, possibly changing how massive objects interact. Our models of planetary motion, galaxy formation, and even the overall structure of the universe would need to be overhauled, potentially forcing us to rethink many fundamental aspects of astrophysics and cosmology. If such a substance were to fill space, it would need to possess certain unique properties. Most importantly, it would have to be incredibly diffuse, spreading its mass over vast, nearly unimaginable volumes. This would prevent it from interfering with the observed motions of celestial bodies. The substance would also have to be nearly invisible to our current detection methods, interacting minimally with electromagnetic radiation. This is why we have yet to observe such a substance, despite the gravitational anomalies observed in galaxies and galaxy clusters. The substance would likely cluster around visible matter, forming halos around galaxies and filaments connecting them. It would help shape the large-scale structure of the universe, potentially explaining some of the mysterious phenomena we observe in the cosmos today. Imagine a substance that could withstand the passage of time on a cosmic scale, existing virtually unscathed for billions of years, showing no sign of decay or transformation into any other type of matter or energy. Such a substance would defy the normal expectations we place on matter in the universe, making it an extraordinary puzzle for scientists. To further complicate its mysterious nature, this substance wouldn't fit into the typical model of matter: no protons, neutrons, or electrons. It would not be composed of the usual atomic building blocks that form the fabric of ordinary matter. It would have to be non-ionic, a state of existence so alien to what we understand from the early moments of the universe and from our study of the cosmic microwave background radiation. At the same time, this hypothetical material would need to interact so weakly with itself and with the visible matter around it that it would leave no lasting trace or structure in the universe. It would neither clump together to form visible objects, nor make its presence obvious in any way. Such a substance would be invisible to our senses, both in terms of sight and touch, and imperceptible to most of the instruments we've developed to explore the cosmos. Together, these unique properties form the foundation of what scientists have come to call dark matter, an elusive, enigmatic substance that continues to challenge everything we thought we knew about the nature of the universe. But even as we struggle to understand the properties of dark matter, another phenomenon remains just as puzzling, if not more so: the behavior of light itself in different environments. We are all familiar with light's ability to travel through a vacuum at a constant speed, approximately 299,792,458 meters per second. But in any other medium, light behaves differently. Whether it passes through glass, water, or even air, light consistently slows down, and this slowdown is more than just a minor curiosity. When light enters a material medium, its photons are absorbed by atoms and molecules. They are then re-emitted in the same direction, but with a slight delay. This interaction takes time, and because the density of the material affects how often these interactions occur, the denser the medium, the more light is slowed. For instance, in water, light travels at about 75% of its speed in a vacuum, and in glass, it moves at about 2/3 of its vacuum speed. Even air, which may seem like a near vacuum, slightly diminishes the speed of light. This fundamental slowing of light can also cause phenomena like refraction, which is why objects appear distorted when submerged in water. And it is the same reason why we see mirages in the desert or on hot roads, as light bends when it encounters areas of air with different temperatures. These effects arise from the changes in the density of air due to temperature differences, creating a ripple effect that distorts our perception of distant objects. Understanding the behavior of light in various mediums is not only a matter of academic curiosity, it has practical applications that impact countless technologies. Fiber optics, which form the backbone of global communication networks, rely on our understanding of how light behaves in glass fibers. Telescopes and microscopes depend on the manipulation of light to magnify distant objects or tiny structures. But light's interactions with the world are not the only forces that affect our universe. Gravity, the force that governs the movement of planets and stars, plays a role in shaping the cosmos that is every bit as profound, but it is also subject to the influence of its environment. In a vacuum, gravity operates according to the principles established by Einstein's theory of general relativity. But in a medium that contains matter, the experience of gravity changes. In environments like air or water, additional forces, such as buoyancy or drag, act on objects, and these forces may distort our perception of gravity's true effects. For instance, an object might appear to float in water, not because gravity has suddenly stopped working, but because the buoyant force of the water pushes upward against it, balancing out the downward pull of gravity. Similarly, objects falling through the air encounter resistance, which limits their speed and alters the way gravity manifests. Even the propagation of gravitational waves, ripples in the fabric of space-time caused by massive objects like black holes or neutron stars, would behave differently in a medium filled with matter. These waves, which normally travel freely through the vacuum of space, would lose energy or change direction when interacting with denser materials. The presence of matter would also modify how gravity interacts with space-time itself. A denser medium could distort gravitational fields, creating complex interactions between objects that would not be present in the vacuum of empty space. But while these effects could complicate our observations and experiments, they would not fundamentally change the nature of gravity itself. Instead, they would add layers of complexity to how we observe and understand the force. As we grapple with the mysteries of light and gravity, another cosmic force, dark energy, further stretches our understanding of the universe. Dark energy, which seems to fill all of space, exerts a strange influence, accelerating the expansion of the universe in ways that challenge everything we thought we knew about the cosmos. Unlike gravity, which pulls matter together, dark energy works to push space apart, speeding up the expansion of the universe rather than slowing it down. This mysterious force is responsible for the observed acceleration in the separation of galaxies, and its discovery has forced us to rethink the past and future of the cosmos. In the beginning, the universe was dominated by matter, both ordinary and dark. But as space expanded, the density of matter decreased, while the density of dark energy remained constant. This shift led to the gradual dominance of dark energy, eventually driving the expansion that we see today. As we peer into the future, dark energy holds the key to the ultimate fate of the universe. If it continues to drive the expansion of space at its current rate, the universe could be headed toward what is known as the Big Freeze. This scenario would see galaxies drifting farther apart, the observable universe growing colder and darker over time, with all of the stars eventually burning out. On the other hand, if dark energy were to increase in strength, it could lead to a catastrophic event known as the Big Rip, where the very fabric of the universe would begin to tear apart, from the largest cosmic structures down to the subatomic particles that make up matter. But perhaps even more profound than the implications of dark energy for the fate of the universe is its effect on the foundations of physics. Dark energy suggests that empty space is not truly empty at all, but instead filled with an intrinsic energy that defies our traditional notions of nothingness. This idea resonates with quantum field theory, which posits that all space is filled with fluctuating energy fields. However, this concept also contradicts our observations of the universe, particularly in terms of the cosmological constant problem. Reconciling these differences could lead to breakthroughs that might unify quantum mechanics with general relativity, and two of the pillars of modern physics that have, so far, remained separate despite their shared goal of describing the forces that govern the universe. The impact of dark energy would only be compounded in a universe filled with a non-vacuum medium, as such a space would fundamentally alter our understanding of dark matter. In our observed universe, the near-empty expanses between stars and galaxies allow light and other forms of radiation to travel unhindered, enabling us to study distant cosmic phenomena. But if space were filled with matter, light's passage through the universe would be obstructed. This added matter could obscure our ability to detect and study dark matter, making it harder to observe the subtle gravitational effects that point to its existence. The gravitational lensing effects we observe today, which provide some of the strongest evidence for dark matter, might be altered or masked by the presence of additional matter in the space between us and the distant objects we seek to study. In such a universe, everything would be different: dark matter, light, gravity, and even dark energy itself. The very way we observe the cosmos would be altered, leaving us to navigate a universe that operates according to laws we have yet to fully comprehend. Furthermore, a non-vacuum space would profoundly affect the movement and distribution of visible matter throughout the universe. The additional friction and interactions created by this medium would dramatically alter key galactic phenomena, like the rotation curves of galaxies and the formation of large-scale structures, which we currently use to support the existence of dark matter. The presence of a substance filling space would change the way we perceive these cosmic phenomena, prompting a complete reevaluation of our models for galaxy formation and evolution. Such a shift could lead to entirely new explanations for the phenomena we currently attribute to dark matter. In essence, this would require us to rebuild our understanding of the universe from the ground up. A non-vacuum space would blur the line between ordinary matter and dark matter, potentially leading to entirely new theories that attempt to unify these two concepts in ways we haven't yet imagined. The implications are profound, as it would alter the very foundation of our cosmological models and challenge our fundamental assumptions about the universe. The presence of matter in space would also have a dramatic impact on planetary orbits. If space were filled with even a thin gas, it would create a drag on planets as they moved through it. This friction would gradually slow down the planets, causing them to spiral inward toward their stars. The outer planets, with their larger orbits, would feel the effect first, and over time, their orbits would decay. The substance filling space would interfere with gravitational interactions in unpredictable ways. Depending on its density, it might dampen or amplify gravitational forces between celestial bodies, potentially destabilizing entire solar systems. Moreover, as planets move through this non-vacuum environment, they would generate heat, potentially creating shock waves. These waves could result in significant changes to planetary atmospheres and surface conditions. Smaller bodies, like asteroids and comets, would be particularly vulnerable, potentially disintegrating as they moved through the resistant medium. The current stability and longevity of our solar system, which relies heavily on the near-perfect vacuum of space, would be compromised. A universe without this vacuum would likely have very different structures, one with shorter-lived and more chaotic planetary systems. The delicate balance that allows for the formation of stable, long-lasting planets capable of supporting life would be disrupted. Without the vacuum of space to maintain the necessary gravitational structure, the stability of solar systems would be drastically affected. Planets, moons, and other celestial bodies would no longer orbit their stars or each other. Instead, they would drift apart, continuing on their current trajectories in straight lines. This would lead to the rapid disintegration of solar systems as we know them. Stars themselves would lose their internal structure, unable to maintain the gravitational forces that hold them together. Without gravity to compress their cores, stars would expand and dissipate into space. The nuclear fusion reactions that power stars would cease, as gravity is essential for maintaining the extreme pressures needed for these processes. The asteroid belts and objects in the Kuiper Belt would disperse, creating an increase in the number of rogue objects hurtling through space. These wandering bodies could pose significant risks to any remaining structures or life forms in the universe. The absence of gravitational stability would not only affect individual solar systems, but also impact larger cosmic structures. Galaxies would lose their characteristic shapes and spiral arms, as stars and gas clouds would no longer be bound together by gravitational forces. The universe would become a vastly different, more chaotic place, with celestial objects moving independently in a cosmic free-for-all. Star formation in a non-vacuum space would also look vastly different from what we observe in our universe. In the cosmos, we know vast, nearly empty regions of space allow gravity to slowly pull together clouds of gas and dust, eventually forming dense cores that give birth to stars. However, in a non-vacuum environment, the process of star formation would face significant challenges. The presence of matter throughout space would interfere with the gravitational collapse needed to form stars. The additional particles in the medium would create resistance, slowing down or even preventing the aggregation of material into stellar nurseries. This interference would make it far more difficult for regions of space to become dense enough to trigger nuclear fusion, the process that powers stars. Furthermore, The omnipresence of matter would disrupt the temperature and pressure conditions crucial for star birth. The environment might be too warm or too cool, breaking the delicate balance required for stellar ignition. The increased pressure from surrounding matter would also impede the compression of gas clouds, a crucial step in star formation. If stars did manage to form in such an environment, they would likely have characteristics very different from those in our universe. Their size, composition, and lifespan could all be altered by the unusual conditions of a non-vacuum space. This scenario underscores the importance of the near vacuum of our universe, not just as an empty space, but as a critical factor in shaping the celestial objects we observe. Black holes, in a space filled with matter, would face a future of continuous growth and evolution. As these cosmic behemoths drift through matter-rich regions, their immense gravitational pull would draw in surrounding material, steadily increasing their mass and size. This process, known as accretion, would cause black holes to become ever more massive over time. The influx of matter would not be a quiet affair. As material spirals towards a black hole, it forms a swirling disk of superheated gas and dust. This accretion disk would generate intense radiation and potentially power massive jets of energy and particles, making black holes some of the brightest objects in the universe. Over incredibly long timescales, these black holes could potentially merge with other black holes they encounter, leading to even larger entities. This process of growth and merging could result in the formation of supermassive black holes, similar to those found at the centers of galaxies. However, this growth is not endless. As black holes consume the available matter in their vicinity, they would eventually exhaust their local food supply. At this point, their growth would slow down and they would rely on chance encounters with new sources of matter to continue expanding. The ultimate fate of these black holes would depend on the long-term evolution of the universe itself and the nature of dark energy in a non-vacuum environment. In a universe without a vacuum, galaxies would evolve in ways that fundamentally differ from our current understanding. The presence of matter or energy filling the space between celestial objects would alter the dynamics of galactic formation and evolution. First, the additional matter or energy would significantly affect gravitational interactions. Galaxies would experience increased drag as they move through this medium, slowing their rotation and distorting their shapes. The iconic spiral arms we observe in many galaxies might not form at all, or would appear heavily distorted due to this resistance. The intergalactic medium would also impact the process of star formation. The additional material could provide more fuel for star birth, potentially leading to more rapid and intense periods of star formation. However, it could also interfere with the delicate balance of gas dynamics within galaxies, disrupting the normal cycles of stellar birth and death. The evolution of supermassive black holes at the centers of galaxies would be similarly impacted. The constant influx of material from the surrounding medium could lead to more rapid growth of these cosmic giants, potentially resulting in larger and more numerous black holes throughout the universe. This non-vacuum environment would reshape our understanding of galactic evolution, challenging many of the models and theories we currently use to explain the cosmos. In a universe without a vacuum, cosmic voids, those vast, nearly empty regions of space, would cease to exist as we know them. These regions, which punctuate the cosmic web, would be fundamentally altered. Instead of being nearly devoid of matter, these areas would be filled with some form of substance or medium. This hypothetical universe would likely be much denser overall, as the absence of a vacuum would mean that space itself would be occupied by matter or energy of some kind. This could dramatically change the distribution of galaxies and other cosmic structures. The contrast between the densest regions of space and the least dense would be far less pronounced. The behavior of light and other forms of electromagnetic radiation would be significantly different in such a universe. In the absence of a vacuum, these waves would interact constantly with the pervasive medium, potentially altering their properties as they travel. This could have profound implications for how we observe and understand the cosmos, reshaping our very perception of the universe itself. In a universe where space is not a vacuum, the fundamental processes that shape the cosmos would be radically transformed, altering the very nature of celestial bodies and space travel. The familiar vast emptiness of the universe, which we currently recognize as the vacuum of space, would no longer be a featureless void, but instead a medium filled with matter. This ubiquitous presence of particles, gases, and other substances would create a dramatic shift in how stars, planets, and galaxies form and evolve. The universe, as we understand it, would be unrecognizable, with cosmic voids, the seemingly empty expanses between galaxies, being rendered obsolete, and the life cycles of stars undergoing profound changes. In our current universe, stars are born from the gravitational collapse of vast clouds of gas and dust that exist in near-perfect vacuum conditions. However, in a universe devoid of this vacuum, star formation would be hindered by the surrounding medium. The collapse of these clouds would be obstructed by the presence of matter filling the space, potentially preventing stars from forming altogether, or altering their initial mass and composition in unpredictable ways. This interference from the surrounding medium would not stop once stars have formed. The very processes that sustain stars, nuclear fusion, which generates heat and pressure at their cores, would be disrupted by the matter around them. In a non-vacuum environment, the energy produced by nuclear fusion would not radiate freely into the vast emptiness, but would instead be absorbed and scattered by the surrounding substance. This would cause the star to lose its internal balance, potentially altering its lifespan, temperature, and overall behavior. The medium surrounding stars would also have a profound impact on stellar evolution. Stellar winds, streams of charged particles ejected by the star, would be affected, and mass loss, which plays a critical role in a star's life cycle, could occur at different rates or even in completely new forms. The interaction between the star and the surrounding medium would likely generate friction, slowing the star's rotation and altering its magnetic properties. This could fundamentally change the nature of stellar phenomena, such as sunspots, solar flares, and coronal mass ejections, which are crucial to our understanding of stellar activity and the solar system's environment. Beyond the stars themselves, the absence of a vacuum would significantly alter space travel. Currently, spacecraft glide effortlessly through the vacuum of space, encountering little resistance. In a universe where space is filled with matter, spacecraft would face considerable drag, like ships moving through water or airplanes flying through the air. This resistance would require spacecraft to use vastly more energy to move through space, making long-distance interstellar travel much more difficult and fuel-intensive. Navigating through a substance-filled space would not only require more energy, but would also change the design of spacecraft. Instead of the boxy or irregularly shaped vehicles designed for the vacuum of space, spacecraft would need to adopt sleeker, more streamlined forms, similar to the aerodynamic shapes used for atmospheric flight, in order to reduce drag and improve fuel efficiency. Communication across vast distances in space would also undergo drastic changes in a non-vacuum universe. Electromagnetic signals, such as radio waves, rely on the absence of matter to travel freely across space. In a medium-filled environment, these signals would be absorbed, scattered, or weakened by the particles around them. This would limit the range and clarity of transmissions, making communication between Earth and distant spacecraft or celestial bodies significantly more challenging. To overcome this, new communication methods would likely need to be developed, such as creating a network of relay stations spread across space to maintain consistent contact. Furthermore, the fundamental principles of celestial mechanics, how planets, stars, and galaxies move and interact with one another, would be reshaped. The presence of matter in what was once the vacuum would alter the dynamics of orbits, trajectories, and gravitational interactions. This new cosmic environment would demand a complete reevaluation of current models of galactic evolution and orbital dynamics. For astronomers and physicists, it would open up entirely new avenues of research and necessitate a comprehensive redesign of our space exploration strategies and technologies. The challenges presented by this environment would push humanity to find innovative solutions for navigating and understanding the cosmos. Astronauts venturing into space would face an entirely new set of challenges in a non-vacuum universe. The absence of a vacuum would mean that space is no longer the silent, featureless expanse that we are accustomed to, but a dynamic, particle-filled environment. One of the primary concerns would be the atmospheric pressure acting on both the astronauts and their equipment. In this new environment, astronauts would need to contend with external forces pushing against their bodies, requiring the development of new spacesuit designs to withstand these pressures, while keeping the internal pressure and conditions stable for the astronaut. The added presence of matter in space would also make propulsion and navigation significantly more complex. Just as vehicles on Earth encounter drag from air, spacecraft in a non-vacuum universe would experience drag from the particles or gases present. This resistance would affect the maneuverability of spacecraft, potentially making travel more fuel-intensive and requiring new technologies for efficient propulsion. Traditional rocket engines, while effective for launching into space, would be far less efficient for sustained travel through a medium-filled environment. This might necessitate the development of hybrid propulsion systems that combine rocket engines for initial ascension with air-breathing jet engines for travel through denser layers of matter, enabling more efficient navigation. Thermal management would become an increasingly important challenge for spacecraft. In a vacuum, spacecraft experience minimal friction, but in a non-vacuum environment, the particles surrounding the craft would generate heat as the spacecraft moves through them. This friction-induced heating would require advanced heat shields and cooling systems to protect the spacecraft from extreme temperatures. The constant interaction with the surrounding medium could also pose new risks, such as the potential for corrosion, contamination, or even the introduction of microbial life into the spacecraft. These new threats would require the development of novel protocols for sample collection, exploration, and the sterilization of equipment to ensure the safety of both astronauts and the spacecraft. All of these changes would fundamentally alter our approach to space exploration. While the challenges of navigating a non-vacuum universe would be immense, they would also open up new scientific opportunities, forcing humanity to rethink its technological approaches to space travel and cosmic exploration. We would need to develop new spacecraft designs, advanced propulsion systems, and novel communication methods to overcome the obstacles of a medium-filled universe. In the process, we would not only expand our understanding of the cosmos, but also gain new insights into the forces that shape the universe and our place within it. In the vastness of space, where the known laws of physics govern celestial bodies, the challenge of constructing a spacecraft capable of navigating such an environment becomes a monumental task. The materials used in construction must withstand the extreme conditions found both in the void of space and during atmospheric flight. The balance required to ensure these materials possess sufficient strength, thermal resistance, and weight efficiency is delicate. Engineers would have to design structures that can endure the vacuum of space, while also managing the stresses encountered when entering and leaving planetary atmospheres. These materials would need to be both lightweight and resilient, able to resist the harsh conditions of space travel, from the intense heat of atmospheric reentry to the bone-chilling cold of the cosmos. Furthermore, their ability to manage heat, retain structural integrity under stress, and adapt to the changing conditions of space would be vital. Traditional propulsion systems, such as chemical rockets, have long been the cornerstone of space exploration. However, these methods face significant limitations when venturing beyond the confines of Earth's atmosphere. The reliance on carrying large amounts of fuel, which burns through rapidly, makes long-distance space travel inefficient and unsustainable. This reality forces us to look toward alternative propulsion systems that could be more adaptable, especially in regions where resources are scarce. Among the most promising of these alternatives is the Bussard ramjet, a theoretical spacecraft propulsion system that collects interstellar hydrogen by using an immense electromagnetic field. This hydrogen would then be funneled into a fusion reactor, where it would undergo a nuclear fusion process. By utilizing the very matter surrounding the spacecraft, the Bussard ramjet could produce continuous thrust over vast distances, making it a powerful contender for future space exploration. Another cutting-edge propulsion method involves the magnetic sail, a concept that would revolutionize space travel. A magnetic sail would work by generating a powerful magnetic field capable of deflecting charged particles in the interstellar medium. As these particles are pushed away by the sail, the spacecraft would experience a forward thrust. This method does not require onboard fuel and could be highly efficient in areas of space that have higher particle densities, such as near certain stars or nebula. In these regions, the magnetic sail could operate almost perpetually, harnessing the natural energy of space itself to propel the spacecraft forward. Similarly, laser-powered propulsion offers another intriguing possibility. Using intense lasers, spacecraft could ionize and heat the surrounding matter, converting it into plasma that would be expelled from the spacecraft as exhaust, generating thrust. This method would combine the advantages of external fuel with the precise control inherent in directed energy systems, opening up new realms of propulsion potential. However, the challenges facing deep space missions are not limited to propulsion. Communication across vast interstellar distances would face tremendous hurdles. As the universe expands at an accelerating rate due to the presence of dark energy, the distances between celestial bodies increase ever more rapidly. This phenomenon, while awe-inspiring, presents a significant obstacle for any mission seeking to maintain communication with Earth. The problem is compounded by the effects of redshift, a process where electromagnetic waves stretch and weaken as they travel through expanding space. This stretching of signals would make it increasingly difficult to maintain clear, reliable communication with distant spacecraft or colonies on other planets. Additionally, as the universe continues to expand, the time delays inherent in communication would only grow. Signals that once took years to travel might now take decades, centuries, or more. The practical impact of this would be profound, potentially rendering real-time communication or even near real-time impossible for missions beyond our local solar neighborhood. The power required to send these signals across such vast distances would also increase significantly, demanding more advanced communication equipment and greater energy reserves on space missions, thus adding complexity and cost to any deep space endeavor. In the hypothetical scenario where space is not a vacuum, but rather a medium filled with matter, the very nature of space exploration would shift dramatically. With a tangible substance present, spacecraft could operate in entirely new ways. Propulsion systems, for example, could become more efficient, eliminating the need to carry oxidizers. This would make spacecraft lighter and more maneuverable, allowing for larger payloads and longer missions. The presence of a medium would also open the door for new communication methods. Sound waves, which are currently unusable in the vacuum of space, might become viable for long-distance communication in such an environment, offering a faster and more reliable alternative to electromagnetic wave transmission. These developments would transform how we think about space exploration and the technologies required to sustain it. Additionally, this non-vacuum environment could provide a natural form of shielding from harmful cosmic radiation. Currently, spacecraft and space habitats are built with thick layers of protective materials to shield their inhabitants from the intense radiation emanating from the sun and other cosmic sources. With a medium present, the risks of radiation exposure might be significantly reduced, making long-duration missions and colonization efforts far more feasible. This new environment could also unlock the possibility of in-situ resource gathering. Spacecraft could harvest and process materials directly from their surroundings, effectively allowing them to refuel and resupply while on the move. This ability would drastically extend the reach of space exploration, allowing us to travel farther without the need to return to Earth for resources or establish outposts in distant locations. The design of space stations and habitats for extended stays in deep space would need to evolve to meet the new challenges presented by this non-vacuum space. One of the most pressing concerns would be the creation of robust radiation shielding. The materials used for constructing space stations would need to be significantly thicker, more durable, and resistant to the damaging effects of cosmic rays and solar radiation. Life support systems would also need to be far more advanced, capable of recycling air, water, and waste with near-perfect efficiency over extended periods. Artificial gravity, likely generated through rotating sections of the habitat, would be a crucial feature. This centrifugal force would simulate Earth-like gravity, preventing muscle atrophy and bone loss, two common health issues associated with long-term exposure to microgravity. The psychological well-being of astronauts would also be a key factor in the design of future space habitats. To combat isolation, these habitats would feature larger living spaces, private quarters, and communal areas. Virtual reality systems could also be employed to simulate Earth-like environments, maintaining crew morale and combating the mental strain of deep space travel. As the vision for space exploration becomes more ambitious, the need for self-sufficient habitats would become more urgent. Future space stations and colonies would need to be able to produce their own food, provide medical care, and maintain equipment without constant resupply from Earth. Advanced 3D printing technology would play a pivotal role in this endeavor, enabling the production of replacement parts and tools on site. This autonomy would be essential for long-term space missions and colonization efforts, providing the flexibility necessary to explore distant regions of space without relying on Earth-based resources. If space were not a vacuum, the very nature of life on Earth would change as well. Without the vacuum that currently separates our atmosphere from the cosmos, Earth's air would begin to diffuse into space. Gradually, the gases that make up our atmosphere, oxygen, nitrogen, and carbon dioxide, would mix with the surrounding matter, causing our planet's protective layer to thin out. The loss of atmospheric pressure would make breathing difficult, and over time, the atmosphere would no longer provide adequate protection from the sun's harmful radiation. The delicate balance of gases that currently sustains life on Earth could be disrupted, potentially changing the very chemistry of our atmosphere. With new gases or particles mixing with our air, the ozone layer's ability to protect us from ultraviolet radiation could be compromised, leading to unforeseen consequences for all life on Earth. In this imagined scenario, the interplay between the non-vacuum environment of space and the future of human exploration would transform both our understanding of the cosmos and our ability to live within it. New technologies would emerge, new challenges would arise, and humanity would continue its journey into the great unknown, striving to push the boundaries of what we know and what we can achieve. The possibilities would be boundless, and the future of space exploration would never be the same again. If space were not a vast vacuum, many of Earth's weather patterns and climate systems would be fundamentally transformed. The properties of Earth's atmosphere and its interactions with the surrounding void play a critical role in maintaining the balance of natural phenomena on our planet. Were space to be filled with matter, many of these processes, such as the water cycle, wind patterns, and temperature regulation, would be drastically altered. Such an alteration could result in a vastly different and likely hostile environment for life on Earth. The intricate balance that allows the Earth to support life could be disrupted, giving rise to conditions far more severe and inhospitable than what we experience today. As the sun expands into a red giant in the distant future, Earth's magnetic field would experience major changes. The sun's increased heat and radiation would influence the internal processes of our planet's core, particularly those responsible for generating the magnetic field. The core, a churning mass of liquid iron and nickel, might see changes in its convection patterns and electrical conductivity. This would likely weaken Earth's magnetic field, diminishing its protective capabilities against solar and cosmic radiation. The magnetic poles themselves could shift more rapidly or even flip more frequently, leading to a more erratic and unstable magnetic field. Without the strong shield we currently have, more solar wind and cosmic radiation would reach Earth's surface, escalating radiation exposure and potentially creating hazardous conditions for living organisms. This weakened magnetic field would also have profound effects on Earth's magnetosphere, the region around the planet influenced by its magnetic field. As this region shrank and compressed, particularly on the sun-facing side, the natural protective barrier against charged particles would weaken. Auroras, usually confined to the polar regions, could begin to appear at much lower latitudes, as the magnetic field lines, which typically guide these phenomena, shift. With increased radiation reaching Earth's surface, the risks to life forms that are not adapted to such intense conditions would multiply, potentially driving rapid evolutionary changes or even mass extinctions. In addition, navigation systems reliant on magnetic orientation would be disrupted and migratory animals could lose their bearings, throwing ecosystems into turmoil. The shift in Earth's characteristics would also radically alter weather patterns. If, for example, Earth's rotation slowed down, the result would be longer days and nights, bringing about extreme temperature fluctuations. These changes would likely disrupt the patterns of global wind circulation, leading to the formation of larger and more powerful storm systems. In contrast, a faster rotation could lead to shorter days and nights, with rapid transitions between day and night, potentially affecting biological rhythms and climate systems. Similarly, variations in Earth's axial tilt, which determines seasonal changes, would have a significant impact. A greater tilt could lead to more extreme seasons, scorching summers and freezing winters, while a lesser tilt could produce milder seasons. Such shifts would alter precipitation patterns, potentially transforming lush regions into arid deserts or converting dry areas into fertile lands. Earth's orbit around the Sun also plays a vital role in determining weather patterns. A more elliptical orbit could cause significant fluctuations in global temperatures, leading to periods of global cooling and warming. These changes could affect sea levels, disrupt the distribution of plant and animal species, and alter ocean currents and atmospheric circulation patterns. Even today, human-induced climate change, driven largely by the increased emission of greenhouse gases, has begun to affect Earth's climate systems. As global temperatures rise, we are witnessing more frequent and intense extreme weather events, such as heat waves, droughts, and powerful storms. This underscores the fragile balance of Earth's climate and the far-reaching consequences of even minor alterations to the planet's characteristics. In a world where space is filled with matter, the behavior of the ozone layer would also be dramatically different. The ozone layer, which shields life on Earth from harmful ultraviolet radiation, would be far less stable in a non-vacuum environment. The ozone molecules themselves are inherently unstable, and their formation and breakdown are delicately balanced. In a universe filled with matter, the presence of various gases could significantly alter ozone chemistry. For instance, if nitrogen or hydrogen were present in space, new compounds like nitrogen oxides or hydroxy radicals might form, further complicating the dynamics of ozone creation and destruction. Temperature would also play a crucial role in these reactions, as ozone formation and destruction are highly temperature-dependent processes. In a non-vacuum space environment, temperature fluctuations could lead to regions of ozone depletion or accumulation, potentially exacerbating environmental instability. The effect of a matter-filled universe on climate change would extend far beyond Earth's atmosphere. In such an environment, the movement of energy across cosmic distances would be drastically altered. A denser medium of matter in space would absorb, scatter, and reflect more of the radiation emitted by stars, potentially reducing the amount of solar energy that reaches planetary surfaces. This reduction in energy would have far-reaching consequences, potentially cooling planetary climates and altering weather patterns in ways that we cannot yet fully predict. Additionally, the higher density of cosmic matter could lead to more frequent impacts with dust, gas, and small celestial objects, triggering sudden and violent climate shifts. These impacts might destabilize planetary weather systems, making them more unpredictable and chaotic. Changes in planetary magnetic fields influenced by the presence of matter in space could also exacerbate the effects of such cosmic disturbances. Planetary magnetic fields are crucial in shielding atmospheres from harmful radiation. With a denser space environment, these protective shields might weaken or shift, exposing planets to higher levels of cosmic radiation. The resulting changes in atmospheric chemistry could have unpredictable effects on climate, further complicating the relationship between cosmic matter and planetary environments. The interplay between these factors, cosmic matter, planetary magnetic fields, and atmospheric systems, would create an ever-changing cosmic environment, one that would challenge our understanding of climate dynamics. Finally, Earth's day-night cycle could undergo profound changes if the planet's rotation were altered. Earth's current 24-hour rotation period gives rise to our familiar pattern of daylight and darkness, crucial for regulating biological processes on Earth. If Earth's rotation were faster, we would experience shorter days and nights. This could disrupt the delicate balance of biological cycles, causing rapid transitions between light and dark that many species are not adapted to. Similarly, if Earth's rotation were to slow, the longer days and nights could disrupt existing ecosystems and the behaviors of organisms that depend on more regular cycles of daylight and darkness. The interaction between these changes and the Earth's climate systems would undoubtedly lead to new and unexpected challenges for life on our planet. If Earth's rotation were to slow down, the consequences would be far-reaching and dramatic. Picture a world where the length of our days and nights stretches out beyond anything we currently know. Sunlight could last for days, uninterrupted, before being replaced by equally long periods of darkness. This shift in the Earth's rotation would spark extreme temperature variations across the globe. On the sunlit side of the planet, temperatures would rise to unbearable levels, while the dark side would plunge into a chilling cold. These shifts would throw the entire planetary climate into disarray, affecting everything from weather patterns and ocean currents to the balance of ecosystems around the world. The length of days and nights directly influences the climate. If the Earth spun faster, it would likely lead to more powerful winds and intense storms. The atmosphere would struggle to keep up with the rapid rotation, creating chaos in weather systems. On the flip side, a slower rotation would probably result in more stable weather, but it could also cause significant temperature differences between the equator and the poles. These changes could drastically alter ecosystems, challenging everything from the natural world to human society. Our daily routines, which are so closely tied to the 24-hour cycle, would require massive adjustment. The structure of our lives, our sleep patterns, work schedules, and even how we build and organize our communities would all need to adapt to a radically different world. It would highlight just how essential Earth's current rotation is to the rhythms that sustain life as we know it. The tilt of Earth's axis also plays a vital role in shaping our climate. Currently, the planet's axial tilt is about 23.5 degrees, which gives us the cycle of seasons we are familiar with: spring, summer, autumn, and winter. However, any significant change in this tilt would disrupt this delicate balance. If the tilt were to become more extreme, we would see seasons intensify. Summers would scorch the earth, while winters would become brutal, plunging regions into extreme cold. The tropics could expand further from the equator, transforming temperate zones into sweltering hot regions. On the other hand, areas closer to the poles could experience bizarre patterns of light and darkness, with months of constant daylight or perpetual night. Conversely, a reduced axial tilt would result in milder seasons. The sharp contrast between summer and winter would diminish, which could have profound impacts on agriculture and ecosystems that rely on seasonal changes. This shift would likely cause some regions to experience almost constant conditions, leading to new patterns in weather and precipitation. Such alterations would force life on Earth to adapt. Plants and animals would have to evolve to cope with the new climate patterns. Migration routes could shift as species move in search of more hospitable conditions. Human activities, everything from farming to urban planning, would also need to evolve to accommodate these changes. The shifts in climate would challenge the very foundation of Earth's biodiversity, forcing organisms to find new ways to survive in an ever-changing environment. If Earth's organisms were to encounter a non-vacuum space environment, the challenges would be even more profound. Life forms that evolved in Earth's atmosphere would face a completely different set of conditions, such as varying gases, liquids, or even more exotic states of matter. The most immediate concern would be respiration. Earth's life forms are accustomed to breathing oxygen in a nitrogen-rich atmosphere. In a different gaseous environment, organisms would need to adapt to extract whatever elements are available for breathing. This could require the development of entirely new organs or changes to cellular metabolism. Another significant challenge would be pressure. A non-vacuum environment could present pressures far greater than those experienced on Earth's surface. Life forms would need to evolve to withstand these forces, potentially resulting in more compact body shapes or the development of internal support systems. Movement through a denser medium would also require major adaptations. Organisms might need to develop fin-like structures to swim or wing-like appendages to fly through thick atmospheres. Additionally, the sensory organs of these life forms would need to evolve to perceive their surroundings in entirely new ways, further complicating the adaptations required for survival. As our planet continues to evolve, the pressure on Earth's ecosystems grows stronger. Climate change is altering habitats at an unprecedented rate. As temperatures rise, many species are being forced to migrate in search of cooler environments or higher elevations. This migration causes rippling effects through food chains, as predators and prey must adapt to new competition and changing conditions. Ocean acidification, driven by rising carbon dioxide levels, is another major issue. As more CO2 dissolves into the oceans, the waters become more acidic, posing a grave threat to marine life, particularly those organisms with calcium carbonate shells or skeletons. These creatures would need to evolve rapidly to survive in this increasingly hostile environment or risk extinction. Human activity is not just altering the climate, but is also driving evolutionary processes in unexpected ways. Urbanization has created new niches for species that thrive in human-dominated landscapes. Some birds have evolved shorter wings to navigate city environments, while certain plants have begun producing seeds that can better survive in urban conditions, such as on concrete surfaces. The widespread use of antibiotics and pesticides is also having a significant impact, leading to the rapid evolution of resistance in bacteria and insects. This ongoing arms race between human technological advances and nature's adaptability is a stark reminder of the complex relationship between us and the countless other species we share the planet with. In a space environment, the absence of a vacuum would have profound effects on genetic mutations. Organisms in space are constantly exposed to intense radiation, including cosmic rays and high-energy particles. This radiation can damage DNA, leading to an increase in genetic mutations. Without the vacuum of space, organisms would be shielded from much of this harmful radiation. The atmosphere of a planet or the protective layers of a space habitat would absorb or deflect many of the high-energy particles that typically bombard objects in space. As a result, there would likely be fewer radiation-induced mutations. However, the absence of a vacuum could introduce new forms of environmental stress. For example, organisms could be exposed to different types of mutagens, such as ultraviolet radiation or chemical pollutants, which could induce entirely different patterns of genetic changes compared to those induced by space radiation. These changes, whether they are driven by a slowing Earth, shifting axial tilt, or the absence of a space vacuum, highlight the delicate balance that sustains life on Earth. Whether on our planet or beyond, the forces of nature and evolution continue to shape the survival strategies of all living organisms. In a universe where an atmosphere or other forms of protective environments exist, the potential for life to survive and reproduce becomes significantly higher, even for organisms that would not be able to withstand the harsh vacuum of space. The presence of such environments offers a sanctuary where genetic mutations, often lethal in the vacuum of space, might instead become part of the evolutionary process. Over time, this would allow for a greater diversity of genetic variations, increasing the chances of life adapting to entirely new and extreme conditions. In a universe without the vacuum of space, the possibilities for the evolution of extremophiles, organisms that thrive under extreme conditions, could be nothing short of extraordinary. Life could evolve to survive and flourish in environments far beyond anything seen on Earth, unlocking new realms of biological potential. One fascinating possibility is the evolution of extremophiles capable of thriving in ultra-high pressure environments. Such organisms could develop in the extreme depths of ocean worlds or within the intense gravitational forces at the cores of gas giants. These environments are characterized by pressures that are thousands of times greater than those found in Earth's deepest oceanic trenches. To survive, these organisms might evolve unique cellular structures capable of withstanding these immense forces. These adaptations could involve the use of exotic materials or the development of novel molecular arrangements, making them entirely different from any life forms we know today. Another intriguing prospect is the emergence of extremophiles that could flourish in environments saturated with extreme electromagnetic forces. In a universe teeming with matter, intense magnetic fields, radiation belts, or other forms of energetic forces might be far more common than on Earth. Life forms in such environments could evolve mechanisms to either shield themselves from these potent forces or harness them as a source of energy. They might develop unique biological structures capable of absorbing and utilizing electromagnetic radiation, allowing them to power their metabolic processes or protect themselves from harmful radiation. Further expanding on the boundaries of life's potential, one could imagine organisms evolving to exist within exotic states of matter. Life might adapt to exist within superfluids or even Bose-Einstein condensates, states of matter that occur at near absolute zero temperatures. These life forms could develop unique biologies capable of functioning in these quantum realms, where traditional biological processes are rendered entirely foreign. The very concept of what constitutes life itself would be challenged, as these organisms might operate on principles of physics completely different from our own understanding. In such a universe, the likelihood of panspermia, the theory that life could spread across space by hitching rides on asteroids, comets, or other celestial bodies, would be greatly enhanced. A universe rich in matter would likely have a much higher number of planets, moons, and other celestial bodies capable of harboring life. This abundance of potential habitats would decrease the vast distances that life-bearing material would need to travel, improving the chances of successful interplanetary and interstellar transfers of life. Furthermore, a matter-rich universe would also lead to more frequent collisions and interactions between celestial bodies, events that could eject material from life-bearing worlds into space and potentially onto other habitable planets. The frequency of these events would increase the likelihood that life could spread across vast regions of space. Additionally, the presence of more matter in the universe would contribute to an increased amount of interstellar dust and gas. This cosmic material could serve as a protective shield for microorganisms during their journeys through the inhospitable void of space. These tiny life forms could be shielded from harmful radiation and extreme temperatures, greatly improving their chances of surviving the harsh conditions of interstellar travel. The discovery of a parallel universe would radically shift our approach to the search for extraterrestrial life. The confirmation of such a revelation would expand our current understanding of what constitutes life and where it might exist. No longer would scientists need to focus solely on the conditions within our own universe, but also consider the possibility of life thriving in entirely different cosmic environments, subject to different sets of physical laws. This discovery would not only challenge the limits of our scientific knowledge, but could also inspire the development of new theories on the origin of life itself. Could life have originated independently in multiple universes, or might there be a common source that spans across all of existence? Researchers would likely explore the potential for life forms that differ radically from anything we know. These beings would be adapted to the unique physical conditions of their respective universes, leading to the emergence of entirely novel biological systems. The methods and technologies used to search for extraterrestrial life would also evolve as scientists develop new instruments capable of detecting signs of life across dimensional boundaries. They might even delve into quantum phenomena and other advanced physics concepts, bridging the gap between universes and revolutionizing how we search for life beyond our own. As the search for life in parallel universes progresses, it would become clear that intelligent life might also face drastically different evolutionary pressures. The presence of a medium filling all of space would alter the laws of physics and influence the development of celestial bodies. In such a universe, organisms might evolve entirely new methods of locomotion, possibly developing streamlined bodies or propulsion systems designed to navigate this omnipresent medium. Communication among intelligent species could also take on forms previously unimaginable, potentially using waves or vibrations in this universal medium rather than electromagnetic signals. The constant interaction with the space-filling substance could lead to the evolution of highly specialized sensory organs, allowing life forms to detect subtle changes in density or composition. This would provide them with an extraordinary ability to navigate their environment in ways beyond our comprehension. Intelligence, in this context, would likely be focused on understanding and manipulating the properties of the universal medium, enabling advanced civilizations to develop technologies that transcend anything possible in a vacuum-dominated universe. Technological advancements would also be influenced by the properties of this omnipresent substance. Space travel, for instance, would no longer involve overcoming the challenges of vacuum, but would instead require overcoming the resistance of the universal medium itself. Energy production and transmission would take on entirely new forms, potentially exploiting the unique properties of this medium to provide novel power sources and distribution methods. Such advancements would shape the growth of civilizations in profoundly different ways than we could ever imagine. Energy transfer across cosmic distances would change dramatically in a universe where space is not a vacuum. The presence of matter would significantly alter how light, heat, and other forms of energy move through space. Electromagnetic radiation, for example, would interact with particles, losing energy as it travels. This would cause light from distant stars and galaxies to dim much faster, limiting our ability to observe the far reaches of the universe. Heat transfer would also be affected, with conduction and convection becoming viable methods alongside radiation. Shockwaves from events like supernovas would propagate differently, possibly altering the dynamics of these cosmic events. In such a universe, the evolution of celestial bodies would follow a radically different trajectory. Stars might form and die in ways that differ from the processes we observe in our own universe. Galaxies could evolve along alternate paths, and the cosmic web of matter could take on an entirely new structure, influenced by the presence of matter in space. A universe filled with matter would offer the potential for numerous energy sources that future civilizations could harness. Cosmic rays, high-energy particles traveling at nearly the speed of light, could provide an abundant source of power. Advanced technologies might capture and convert this energy into usable forms, enabling a virtually limitless supply of power for space exploration and habitation. Similarly, dark matter, though still poorly understood, is believed to make up a significant portion of the universe. Future scientific breakthroughs could allow us to detect and interact with dark matter particles, unlocking new realms of energy production. The interstellar medium, composed of gas and dust, could also serve as a valuable resource. By developing innovative methods to capture and process this diffuse material, future spacecraft might refuel themselves during long journeys through space, making self-sustaining colonies and extended missions a reality. In addition, the intense magnetic fields and plasma environments surrounding neutron stars and black holes might provide other untapped energy sources. Though far beyond our current technological capabilities, advanced civilizations might one day harness the incredible power of these extreme cosmic phenomena for interstellar travel or to meet their growing energy needs. In the vicinity of a black hole, energy collection methods would undergo significant changes due to the extreme gravitational fields. Solar panels, for instance, would experience extreme time dilation and redshift effects, diminishing their ability to collect energy. However, the accretion disk surrounding a black hole could serve as an alternative, providing a potent source of radiation that might be harnessed for energy, although doing so would require technology far beyond what we possess today. In a universe with different fundamental constants, nuclear energy production would face new challenges. The processes that underpin nuclear reactions depend on the strength of the nuclear force and electromagnetic interactions. Alterations in these forces could fundamentally disrupt nuclear reactions as we know them, rendering current nuclear reactors obsolete or even impossible. Such a universe might present new forms of energy production, forcing future civilizations to rethink their approaches to power generation and energy utilization. Furthermore, alterations in the fundamental constants of nature would profoundly influence the cosmic abundance of elements. The creation of heavy elements like uranium within stars hinges on highly specific physical conditions. If these constants were to change, it could result in a universe with a radically different elemental makeup, one that might not contain the necessary materials for processes like nuclear fission in current reactors. This shift would not only affect fission, but would also have far-reaching consequences on fusion reactions. Our ongoing research into developing sustainable fusion power relies on certain conditions that allow hydrogen isotopes to overcome electrostatic repulsion and fuse. If the fundamental constants were altered, these conditions could either become more favorable or more challenging, reshaping the entire trajectory of nuclear energy research and its potential applications. Moreover, if resource mining were to extend beyond Earth and into space, the nature of such operations would undergo dramatic changes if conducted in a non-vacuum environment. The introduction of an atmosphere would present new challenges and opportunities for extraterrestrial mining. In the vacuum of space, specialized tools are necessary to handle the absence of air and the extreme temperature fluctuations. However, in an environment with an atmosphere, mining methods could more closely resemble those used on Earth. Pneumatic drills, hydraulic systems, and other conventional tools that rely on air or fluid pressure might be adapted for use on other celestial bodies. The presence of an atmosphere would also change how materials are extracted and processed. In the vacuum of space, certain mining techniques leverage the absence of air resistance and the frigid conditions to separate and purify materials. In a non-vacuum setting, these methods would need to be adapted or replaced entirely. On the other hand, the presence of air could allow for entirely new methods, such as separation techniques utilizing air currents or differences in atmospheric pressure. Transporting mined resources would also see a significant transformation. In the vacuum of space, launching materials off-world requires relatively minimal energy, as there is little resistance. However, in an atmospheric environment, overcoming both air resistance and gravity would demand far more powerful propulsion systems. This could potentially make some forms of space mining economically unfeasible, depending on the thickness of the atmosphere and the value of the extracted materials. Yet, these new conditions would open up fascinating possibilities for material formation. Unlike the nearly perfect vacuum of most outer space, non-vacuum environments could foster chemical reactions and molecular interactions that are impossible in a vacuum. One intriguing prospect is the potential for complex organic molecules to form in regions with higher particle densities and diverse elements. In such environments, simple hydrocarbons could combine into more intricate compounds, possibly even organic precursors to life. Another exciting possibility lies in the formation of exotic forms of ice. In non-vacuum conditions, where pressures and temperatures fluctuate, water molecules could crystallize into structures unlike any found on Earth, potentially including high-pressure ice phase or superionic ice, where oxygen atoms form a crystalline structure while hydrogen atoms flow like a liquid metal. Under such conditions, metallic alloys might also emerge by combining in unexpected ways and resulting in materials with extraordinary properties, such as extreme strength, novel electrical conductivity, or entirely new forms of magnetism. Exploring these hypothetical materials could revolutionize our understanding of matter, opening up new frontiers in material science and offering breakthroughs that were previously unimaginable. The study of these unique compounds might not only reshape our technological landscape, but could also inspire innovation in fields ranging from energy storage to advanced manufacturing techniques. The challenges of waste management in space also warrant careful consideration. Unlike on Earth, where waste can be buried, incinerated, or otherwise disposed of, the unique conditions of space, particularly microgravity, demand entirely new approaches. Space stations and spacecraft face the critical task of managing and containing all waste materials, from human waste to food scraps and packaging materials. Water, for example, is an extremely limited resource in space, so astronauts often recycle and purify urine to make it reusable. Solid waste is typically dehydrated and compressed to minimize volume, with compacted waste stored in special containers for eventual disposal. The disposal of waste in space also presents unique risks. Unlike Earth's surface, where waste can be dealt with via landfill or combustion, space debris can threaten spacecraft, satellites, and even entire missions. As a result, Some waste is returned to Earth on supply capsules, while other waste may be jettisoned into space or burned up during re-entry into the atmosphere. Future long-duration missions, such as those heading to Mars, will require even more advanced waste management systems. Scientists are exploring technologies that could recycle or repurpose waste materials, transforming them into useful resources like radiation shielding, fuel, or even building materials. These innovations could have far-reaching impacts not only in space exploration, but also on Earth, where they may offer solutions to sustainability challenges here at home. Time dilation, a fundamental concept from Einstein's theory of relativity, behaves differently in non-vacuum environments compared to the vacuum of space. In environments like Earth's atmosphere or the dense regions of interstellar gas clouds, the presence of matter and energy can significantly alter the passage of time. In a non-vacuum setting, the medium through which light travels is slower than in a perfect vacuum. This effect, known as the refractive index, causes time dilation to manifest more strongly than in empty space. As light slows down while passing through a medium, the local flow of time becomes more pronounced, leading to more noticeable time dilation effects than would be observed in the near-perfect vacuum of outer space. In conclusion, the presence of matter, whether in the form of an atmosphere, particles, or varying pressures, has the potential to fundamentally alter not only our understanding of physical laws, but also the technologies we rely on. From mining to waste management to the very way time itself behaves, these changes offer vast new realms of possibility, some of which could redefine how we approach space exploration, energy production, and even our understanding of the universe itself. Furthermore, the presence of matter within non-vacuum space significantly influences the creation of gravitational fields, which in turn contribute to the phenomenon of time dilation. The denser the matter, the more pronounced the gravitational effect, and consequently, the stronger the time dilation. This means that in regions of space filled with gas, dust, or other forms of matter, time may not flow at a uniform rate. Instead, it could pass more slowly or more quickly, depending on the local density and composition of the surrounding medium. The gravitational fields that arise from these different densities combine with the intricate fabric of space-time, creating a more complex and varied experience of time across different regions of the universe. This understanding reveals that time dilation in non-vacuum space is not a straightforward or uniform phenomenon. Rather, it is intricately tied to the interaction between matter, energy, and the very structure of space-time itself. These interactions lead to the creation of distinct zones where time behaves in unique ways. For instance, near dense regions of space, such as within clusters of galaxies or in the presence of black holes, time may pass at a much slower rate compared to more sparse regions. Such complexities add depth to our comprehension of how time behaves across the vast and diverse environments scattered throughout the cosmos, forcing us to rethink our traditional notions of the passage of time. In a similar vein, the concept of time and its manipulation takes on an even more perplexing nature when viewed through the lens of the twin paradox, a thought experiment that originates from the theory of special relativity. The paradox begins with a seemingly simple scenario. Two identical twins, one who remains on Earth and another who embarks on a high-speed journey through space. According to Einstein's theory of special relativity, the twin who is traveling at high velocities will experience time differently from the twin who stays on Earth. More specifically, time will pass more slowly for the traveling twin compared to their Earthbound counterpart. This phenomenon, known as time dilation, becomes especially evident when the traveling twin returns home after their high-speed journey. Upon reunion, the traveling twin will find that they have aged less than their sibling who remained stationary on Earth. What makes this scenario particularly intriguing is the apparent symmetry of the situation. From the perspective of the traveling twin, it might seem as though it is the Earthbound twin who is moving away at high speed. However, the symmetry is broken when we take into account the need for the traveling twin to change direction and accelerate in order to return home. This acceleration introduces a crucial difference in their respective reference frames. While the Earthbound twin remains in a single inertial reference frame, the traveling twin experiences a shift in their frame of reference due to the change in direction. This asymmetry ultimately resolves the paradox, proving that the traveling twin will indeed age less than the twin who stayed on Earth, thus providing a tangible and measurable demonstration of the real effects of special relativity on the very nature of time. Time dilation is not just a curiosity confined to thought experiments, but a real, observable effect. The practical confirmation of this phenomenon has been achieved through experiments involving highly accurate atomic clocks placed on fast-moving aircraft and satellites. These experiments have shown that clocks in motion tick more slowly than those at rest, validating Einstein's predictions and giving us a deeper, real-world understanding of how time is relative and not absolute. Another fundamental aspect of our universe, tied to the very essence of space-time, is the speed of light. This universal constant, roughly 300 million meters per second, represents the maximum speed at which all matter and energy in the universe can travel. It is not merely a rule governing light, but rather a fundamental limit that shapes the fabric of reality itself. If the speed of light were to change, whether to increase or decrease, the repercussions for the entire universe would be profound and far-reaching. If the speed of light were to increase, it would have a profound impact on the structure of the universe. The fabric of space-time would essentially shrink as information and causality could propagate faster across vast cosmic distances. This could, in theory, allow us to observe parts of the universe that are currently hidden from view beyond the observable horizon. On the other hand, if the speed of light were to decrease, the observable universe would shrink, limiting our ability to study distant cosmic phenomena. A slower speed of light would also have a dramatic impact on fundamental physical laws, potentially altering the nature of mass, energy, and even chemical reactions. Moreover, the famous equation that relates mass and energy, E=mc², would be dramatically affected by such a change. The relationships between energy, mass, and the fundamental processes that govern the universe would require a complete rethinking. The power that fuels stars, the chemical reactions that sustain life, and the very structure of matter itself could all undergo radical transformations. Such a shift would disrupt the delicate balance of forces that govern the universe, potentially unraveling the very laws that sustain our existence. The implications of altering the speed of light extend far beyond theoretical physics. They would challenge the cornerstone of modern physics, general relativity. If, for instance, faster-than-light travel or communication were discovered, it would fundamentally undermine the principle that the speed of light is an unbreachable limit. This would force a re-examination of causality, the idea that cause precedes effect, and lead to a complete overhaul of our understanding of space-time. General relativity could also face significant challenges if new phenomena were observed that deviate from its predictions. For instance, if quantum gravity effects were detected at extremely small scales, effects that contradicted general relativity's predictions, it could point to the need for a more comprehensive theory that unifies gravity with quantum mechanics. Similarly, if gravitational behavior were found to differ from expectations in extreme environments, such as near black holes or during the earliest moments of the universe, it would call into question the completeness of general relativity. Another area where general relativity may need to be revised is in our understanding of dark matter and dark energy. These mysterious substances, which make up most of the universe's mass energy content, are not explained by general relativity. If future discoveries reveal properties of dark matter or dark energy that contradict the theory's predictions, this could lead to a re-evaluation of how gravity operates on cosmic scales, forcing scientists to rethink the fundamental structure of the universe. These challenges to general relativity underscore the need for continued observation and theoretical development in our pursuit of understanding the universe. As new data emerges, we may need to develop entirely new frameworks that can accommodate phenomena that our current theories cannot explain. Gravitational waves, ripples in the fabric of space-time, provide one of the most promising avenues for gaining deeper insights into the universe. These waves travel outward from their source at the speed of light, carrying with them crucial information about some of the most violent and mysterious events in the cosmos. In a space filled with matter, gravitational waves continue to propagate, but their behavior is influenced by the presence of mass and energy in their path. When gravitational waves pass through regions of dense matter, their properties are subtly altered. Large concentrations of mass can deflect or scatter the waves, an effect similar to how light bends around massive objects. This phenomenon, known as gravitational lensing, can change the trajectory of the waves as they travel through space, providing us with valuable clues about the distribution of matter in the universe. Additionally, the amplitude and frequency of the waves may change when they pass through denser regions, although these effects are typically minimal for most forms of matter. Despite their interactions with matter, gravitational waves possess a remarkable property. They can travel through most substances with very little interference. Unlike electromagnetic waves, which can be absorbed or reflected by matter, gravitational waves pass largely unimpeded. This ability to traverse even the densest objects allows them to carry information from the farthest reaches of the universe, from regions of space that are otherwise hidden from view. As such, gravitational waves offer a unique and invaluable window into the workings of the cosmos. By studying these waves, we can gain a deeper understanding of gravity, the structure of space-time, and the most extreme events that occur throughout the universe. If we were able to directly observe the curvature of space-time on a cosmic scale, our understanding of gravity and the very structure of the universe would undergo a monumental transformation. Currently, we can infer the curvature of space-time through indirect methods, such as observing the bending of light around massive objects or studying the orbits of planets. However, if technology were developed that could map and visualize the curvature of space-time across vast cosmic distances, it would completely revolutionize our comprehension of the universe. Such an achievement would allow us to refine our models of galaxy formation and evolution, enabling us to more accurately account for the influence of dark matter and dark energy on the fabric of space-time. It could also reveal unexpected patterns or anomalies in space-time curvature, offering new insights into the fundamental nature of gravity. These discoveries could lead to a deeper understanding of the universe's structure and might even unveil previously unknown cosmic phenomena, reshaping our view of the cosmos in ways we can barely imagine. Furthermore, a more precise understanding of space-time curvature could have profound and far-reaching implications for our exploration of the universe. Such knowledge could lead to the development of highly efficient methods for interstellar travel. Just as ships use ocean currents to chart their courses, we might one day identify optimal paths through curved space-time, significantly enhancing the effectiveness of our journeys across vast cosmic distances. Moreover, this deeper understanding could revolutionize our ability to detect and study gravitational waves, providing unprecedented insights into some of the most cataclysmic events in the universe, such as the mergers of black holes and the explosive deaths of massive stars, known as supernovae. By unraveling the mysteries of space-time curvature, we would not only advance our theoretical grasp of the cosmos, but also uncover practical applications that could redefine the future of cosmic exploration, reshaping our understanding of our place in the universe. In a universe that is not a vacuum, the concept of proper time would undergo significant changes when compared to our traditional understanding in a perfect vacuum. Proper time, the measure of time experienced by an object in its own frame of reference, would be heavily influenced by the presence of matter and energy distributed throughout space. This presence would create gravitational fields and other interactions that would distort the fabric of space-time, causing proper time to behave in ways that are different in various regions of the universe. For example, areas where matter is more densely concentrated would experience stronger gravitational fields, leading to a greater degree of time dilation, causing time to pass more slowly in these regions. On the other hand, areas with less matter would experience weaker gravitational fields and time would flow faster by comparison. Furthermore, the interactions between particles and fields in such a universe would introduce even more complexity to our measurement of proper time. The constant collisions and exchanges of energy between particles could significantly influence the passage of time in their local environment. These dynamic exchanges would lead to variations in how time is experienced across different regions of space. This phenomenon would have profound implications for our understanding of cosmic evolution and the age of the universe. The uneven flow of proper time would make it extraordinarily challenging to establish a consistent cosmic timeline, as different regions of the universe would age at different rates. This complexity would demand a more refined approach to cosmological models and necessitate an entirely new interpretation of observational data from distant cosmic events. Understanding these effects would be key to unlocking a more accurate understanding of how the universe evolves over time. When we consider quantum entanglement, a fundamental concept in quantum mechanics, we find that its behavior changes significantly in non-vacuum environments. In a perfect vacuum, entangled particles interact only with each other, but in a non-vacuum environment, such as Earth's atmosphere or within a liquid, the particles interact with a myriad of surrounding atoms and molecules. These interactions, collectively known as decoherence, can disrupt the delicate quantum states of entangled particles, causing them to lose their quantum properties and behave more like classical particles. As entangled particles collide with other particles in their environment, they exchange information, effectively decohering the quantum system and diminishing the entanglement between them. This process can occur extremely rapidly, often within fractions of a second. However, significant strides have been made in preserving quantum entanglement even in non-vacuum environments. Scientists have developed sophisticated techniques using ultra-cold atoms, trapped ions, and specially engineered materials that create controlled conditions to minimize decoherence. These breakthroughs have opened new possibilities for the practical applications of quantum entanglement in fields like quantum computing and secure communication. The ability to maintain entanglement in real-world conditions is crucial for advancing quantum technologies that could eventually operate beyond the controlled environments of laboratory settings. As research continues, scientists aim to extend the lifespan of entangled states in a variety of environments, bringing us closer to harnessing the full potential of quantum phenomena for everyday applications. The uncertainty principle, one of the cornerstones of quantum mechanics, would remain valid even in a space filled with matter. This principle states that we cannot simultaneously know both the exact position and momentum of a particle with perfect precision. It is a fundamental property of the quantum world, one that is independent of the presence or absence of matter in space. In a matter-filled space, particles would interact more frequently with their surroundings, engaging in collisions or scattering events that reinforce the uncertainty principle. As particles bounce off one another or interact with fields, their positions and momenta would change rapidly and unpredictably, making it even more difficult to measure both properties simultaneously with high accuracy. The presence of matter would add further complexity to quantum systems. For example, particles might become entangled with surrounding matter, further complicating the measurement process. Additionally, the increase in the number of interacting particles would result in more complex quantum states, which could amplify the effects of uncertainty. Nevertheless, despite these practical challenges, the fundamental nature of the uncertainty principle would remain unchanged. It reflects the intrinsic probabilistic nature of the quantum world, regardless of the environment in which quantum particles exist. Finally, the double-slit experiment, a cornerstone of quantum physics, has revealed the wave-particle duality of light and matter. If we were to alter this experiment, the results could shift dramatically, offering new insights into the behavior of the quantum world. One potential modification would involve changing the distance between the slits. As the separation between the slits increases, the interference pattern on the detection screen would expand, resulting in fewer but wider fringes. This subtle adjustment could provide valuable information about the nature of quantum particles and how they interact with their environment, further enriching our understanding of the quantum universe. Conversely, when the slits are moved closer together, a strikingly different phenomenon occurs, one that leads to the creation of a more compact pattern. This new pattern features narrower and more numerous fringes, a direct result of the interaction between light or particles as they pass through the slits. However, the world of quantum mechanics offers even more astonishing alterations. One such modification involves varying the intensity of the light or particle beam. When this intensity is reduced to incredibly low levels, so much so that individual photons or particles are sent through the system one by one, the outcome becomes profoundly intriguing. Despite the dramatic reduction in intensity, the interference pattern still emerges over time, gradually revealing itself as individual particles interact with one another. This observation provides powerful evidence of the quantum nature of reality itself, as each particle appears to interfere with itself in the process. This counterintuitive result is not only unexpected, but also challenges our classical intuitions about the behavior of light and matter. Introducing detectors at the slits to track the path of each individual particle presents yet another fascinating twist in the narrative. When these detectors are used, the interference pattern suddenly vanishes. The very act of observation seems to destroy the interference, a remarkable phenomenon known as quantum decoherence. This shift illustrates how the simple act of measurement or observation can cause the collapse of the particle's wave function, that fundamentally altering the outcome of the experiment. The disappearance of the interference pattern is not merely an anomaly. It reveals the profound and often perplexing nature of quantum mechanics, which remains at odds with the classical physics we encounter in our everyday lives. These modifications, with their strange effects and their profound implications, illustrate just how alien the quantum world can be, constantly challenging and expanding our understanding of reality. Quantum field theory, QFT, serves as the backbone of our understanding of particle physics and the fundamental forces that govern nature. This theory, though highly abstract, has far-reaching consequences, extending well beyond the subatomic scale. It provides a framework for describing the behavior of particles not as individual entities, but as excitations within vast, underlying fields that permeate all of space and time. The fields themselves, though invisible to the naked eye, are constantly at play, creating and destroying particles in a perpetual dance. One of the most profound consequences of quantum field theory is the concept of virtual particles, fluctuations in these fields that occur spontaneously, causing particles to appear and disappear seemingly out of nowhere. Even in what we perceive as empty space, there is a chaotic, teeming presence of activity as these virtual particles emerge and annihilate each other. This means that even a vacuum, the fabric of reality, is anything but empty, brimming with energy and potential. Moreover, quantum field theory offers a new lens through which we can understand the unification of forces. One of the most significant triumphs of QFT has been the successful merging of two of nature's fundamental forces, the electromagnetic force and the weak nuclear force, into a single framework known as the electro-weak interaction. This breakthrough brings us one step closer to the elusive goal of a unified theory that explains all the forces of nature in a single elegant equation. Such a unification is not a mere academic exercise, but holds deep implications for our understanding of the early universe, its birth and evolution. The theory also predicts the existence of antimatter, particles that are mirror images of the particles we are familiar with, and explains the behavior of particles in high-energy collisions. These predictions have been experimentally confirmed multiple times, underscoring the incredible power and precision of quantum field theory in describing the fundamental nature of reality. As scientists continue to refine QFT, there is hope that it may lead to even deeper insights into the very structure of the cosmos. Quantum tunneling, another deeply fascinating phenomenon, plays an essential role in the subatomic realm, but it also carries profound consequences if the fundamental constants of nature were to change. Quantum tunneling allows particles to pass through energy barriers that classical physics would deem insurmountable. In our universe, this effect is crucial, from the process of nuclear fusion in the cores of stars to the functioning of scanning tunneling microscopes, which allow us to visualize individual atoms. But what would happen if the fundamental constants of nature were altered? For instance, if Planck's constant were to become larger, quantum effects would be more pronounced. This might lead to an increased probability of tunneling, fundamentally altering how particles behave at microscopic scales. On the other hand, an increase in the strength of the electromagnetic force would create much higher energy barriers, potentially making tunneling events less likely. Such changes could have catastrophic consequences for stellar evolution, affecting how stars form and evolve, as well as how they produce the elements necessary for life. The delicate balance that governs quantum tunneling underscores the intricate interplay between the constants of nature. These constants, seemingly unchanging, control the behavior of matter at its most basic level. Altering them would reverberate through the entire universe, affecting everything from atomic stability to the processes that power the stars. In the vast expanse of space, far beyond the reach of our familiar vacuum, entirely new quantum phenomena could emerge. As we venture into regions with higher particle densities or stronger electromagnetic fields, quantum effects may manifest in ways we have yet to imagine. One such possibility is the emergence of quantum turbulence, a phenomenon where quantum fluids exhibit chaotic behavior on microscopic scales. This effect could lead to the creation of quantum vortices, tiny whirlpools of particles that behave according to the strange principles of quantum mechanics rather than classical fluid dynamics. The deeper we delve into the quantum world, the more we realize how little we truly understand. In even denser environments, such as those that might exist in the depths of space, quantum entanglement could reach new and unexpected heights. As particles interact more frequently in these regions, they may become entangled over greater distances, creating intricate networks of quantum information. This could radically alter our understanding of quantum communication and computation, especially in the context of space exploration. Additionally, we might witness new quantum phase transitions, where particles in these high-density environments shift between different quantum states, revealing entirely new forms of matter or energy. These discoveries could never be replicated in the vacuum of Earth-based laboratories and could force us to reconsider everything we know about the quantum world. At the heart of quantum mechanics lies the concept of wave-particle duality, the idea that particles can exhibit both wave-like and particle-like properties. This principle, discovered in the early 20th century, has profoundly shaped our understanding of the microscopic world. If, however, our understanding of wave-particle duality were to shift, if new evidence were to emerge that challenged this foundational concept, the implications for physics could be enormous. Such a shift could lead to a complete rethinking of quantum mechanics, forcing us to revise our models of light, matter, and their interactions at the quantum level. This would not only affect our understanding of phenomena like electron diffraction, the photoelectric effect, and the double-slit experiment, but could also have repercussions for other areas of physics, including quantum field theory and particle physics. A major revision of wave-particle duality might require entirely new mathematical frameworks to describe quantum phenomena, potentially paving the way for revolutionary breakthroughs in fields such as quantum computing and cryptography. Despite its profound implications, however, the principle of wave-particle duality has been thoroughly tested and verified over many decades. Any alterations to this foundational idea would require irrefutable experimental evidence and would need to withstand the most rigorous scientific scrutiny before being widely accepted. The Big Bang Theory, which forms the cornerstone of our understanding of the universe's origin, is predicated on the idea of an expanding universe that emerged from an incredibly dense and hot state. Yet, if we were to entertain the concept of a non-vacuum universe, many key aspects of the Big Bang Theory would need to be reconsidered. In such a universe, the presence of matter or energy throughout all of space would fundamentally alter our understanding of cosmic expansion. The current model assumes that space itself is expanding, carrying galaxies along with it. However, in a universe filled with matter, this expansion would be hampered, leading to a vastly different cosmic evolution. Furthermore, the cosmic microwave background radiation, which serves as a crucial piece of evidence for the Big Bang, would need to be reassessed. This radiation, which we observe as a faint glow across the sky, is thought to be the afterglow of the early universe. In a non-vacuum universe, however, this radiation might be scattered or absorbed by the omnipresent matter, altering its properties and forcing us to rethink our understanding of the early cosmos. The formation of large-scale structures, such as galaxies and clusters of galaxies, would also be drastically different in a non-vacuum universe. The gravitational interactions between matter would be far more complex, potentially leading to a universe with a very different appearance than the one we observe today. Scientists would be forced to devise entirely new models to explain how stars, galaxies, and other cosmic structures could form and evolve in such an environment. One of the pillars of modern cosmology, cosmic inflation, would also require significant revision in this new context. Cosmic inflation proposes that the universe underwent a period of rapid expansion in its earliest moments, growing from a subatomic scale to the size of a grapefruit in a fraction of a second. Without inflation, several key puzzles about the universe, including the horizon and flatness problems, would remain unresolved, leaving us to search for entirely new explanations of the cosmos's origins. Furthermore, the origin of cosmic structure would remain an unresolved mystery. Without inflation, we would face the daunting task of explaining how the universe grew to be as complex as it is, with galaxies, clusters of galaxies, and vast structures scattered across the cosmic landscape. Inflation provides an elegant mechanism, a theoretical framework that stretches tiny quantum fluctuations into the large-scale structures we observe today. These fluctuations, seemingly inconsequential on their own, become the seeds from which galaxies and superclusters would eventually form. Without this process, the universe's intricate structure would remain incomprehensible, leaving scientists to look for alternative explanations to account for its incredible complexity. The modification or replacement of cosmic inflation would demand an entirely new paradigm for understanding the cosmos. Our current models, which rest upon the idea of inflation, would no longer hold. Instead, scientists would be thrust into the challenging task of developing entirely new theories. These theories would need to explain the observed uniformity of the universe, its flatness, and the detailed structure of galaxies and matter. Such a shift in our understanding would likely spur a wave of fresh research and could even lead to groundbreaking discoveries, pushing the boundaries of what we know about the universe's origins and the first moments following the Big Bang. At the heart of these theories lies the expansion of the universe, a fundamental process that is shaped by the mysterious force we call dark energy. This expansion influences every aspect of the cosmos, from the grandest galactic clusters to the tiniest atomic interactions. As space itself stretches, galaxies and their clusters are gradually driven apart, a phenomenon first identified by Edwin Hubble in the 1920s. This discovery set the stage for our current understanding of the universe's ongoing expansion, which has profound implications for its ultimate fate. If the rate of expansion were to change, the consequences would be monumental. A faster expansion could lead to a scenario known as the Big Rip, in which the fabric of space would stretch so rapidly that even the most stable objects, such as atoms, would be torn apart. Alternatively, a slower rate of expansion might allow gravity to overcome the force of dark energy, potentially resulting in a big crunch, where all matter collapses back into a singularity. Current observations suggest that the expansion of the universe is actually accelerating, a finding that earned the Nobel Prize in Physics in 2011. This acceleration raises profound questions about the nature of dark energy and its role in shaping the cosmos. As scientists study the acceleration of the universe's expansion, they are piecing together a more detailed picture of the forces at play. Advanced telescopes and powerful computer simulations are critical tools in this effort, allowing researchers to track the movement of galaxies, study the distribution of dark matter, and explore the behavior of cosmic radiation. All of these factors are tied to the expansion, influencing everything from galaxy formation to the cosmic microwave background radiation, the faint afterglow of the Big Bang that still permeates all of space. Understanding the effects of expansion on smaller scales is just as crucial. The ongoing stretching of space influences the formation of galaxies, the distribution of dark matter, and even the temperature fluctuations in the cosmic microwave background. These tiny variations, detectable only with the most sensitive instruments, offer a window into the earliest moments of the universe's history. By studying them, we can unravel the processes that led to the formation of galaxies and other large-scale structures. If we were to imagine the universe in a non-vacuum scenario, where matter or energy fills all of space, the dynamics of cosmic expansion would be radically different from what we currently understand. The presence of such a medium would create resistance and friction, slowing down the motion of celestial bodies. Galaxies, stars, and planets would experience a gradual deceleration, which could eventually lead to earlier mergers and collisions. These interactions could, in turn, accelerate the formation of supermassive black holes, shifting the timeline of galactic evolution in ways we cannot fully predict. The presence of matter throughout space would also have a profound impact on the propagation of light and electromagnetic radiation. Instead of traveling freely through a vacuum, light would be scattered, absorbed, and redshifted to a greater degree, affecting how we observe distant objects. This change would have lasting implications for our understanding of the universe. If matter were to permeate space, it might counteract the effects of dark energy, the very force driving cosmic expansion. This could potentially slow down or even reverse the universe's growth, leading to a dramatic shift in the future. Rather than continuing to expand indefinitely, as current models suggest, the universe could eventually collapse in on itself, culminating in a big crunch. The cosmic microwave background, an essential relic from the universe's early moments, offers another piece of the puzzle. This faint glow of radiation, which permeates all of space, has been cooling steadily since it was first released roughly 380,000 years after the Big Bang. Initially, this radiation had a temperature of about 3,000 Kelvin, but today, billions of years later, it has cooled to just 2.7 Kelvin, slightly above absolute zero. This cooling trend will continue as the universe expands, and the radiation will become progressively colder and fainter. Eventually, the wavelength of this radiation will shift, moving from the visible light spectrum into the microwave region, and eventually further into the radio wave part of the electromagnetic spectrum. The cooling of the cosmic microwave background has other effects as well. As the radiation weakens, the subtle temperature fluctuations that provide critical information about the early universe will become more difficult to measure. These fluctuations are essential for understanding the formation of cosmic structures, such as galaxies and clusters of galaxies. The less we are able to detect these fluctuations, the harder it will be to reconstruct the events that led to the universe's complex structure. Our understanding of the early universe could undergo a dramatic transformation if new evidence or theoretical breakthroughs emerge. Currently, we rely on the Big Bang theory and cosmic inflation to explain the universe's origins and its development over time. However, scientific progress is often driven by the need to challenge and refine existing theories. Advancements in observational technology could enable us to detect phenomena from the earliest moments of the universe, such as direct evidence of inflation or deeper insights into the nature of dark matter and dark energy. These discoveries would provide us with a clearer understanding of the universe's initial conditions and the forces that shaped its evolution. Theoretical breakthroughs could also lead to a rethinking of our understanding of the universe's formation. New mathematical models or concepts in physics might offer alternative explanations for the early stages of the cosmos. These breakthroughs could reconcile the incompatibilities between quantum mechanics and general relativity, shedding light on the fundamental nature of space, time, and the forces that govern the cosmos. Ultimately, refining our understanding of the early universe would have profound implications. It could reshape our comprehension of galaxy formation, the distribution of matter, and even the long-term fate of the universe itself. As our exploration of the cosmos continues, our view of its origins will evolve, leading to deeper insights into the universe's complexity and a greater appreciation for the interconnectedness of all things. If key cosmic parameters were altered, the formation of large-scale structures would be drastically different. For example, in a universe with weaker gravity, matter would not clump together as readily to form galaxies or clusters of galaxies. Instead, the universe might present a more uniform distribution of stars and gas, with fewer dense concentrations. This change in gravity would have a cascading effect, influencing the way galaxies, stars, and even life itself evolved in the cosmos. The very fabric of the universe would be reshaped, and our understanding of its structure would undergo a complete transformation. If dark energy were less dominant, the expansion of the universe would slow down more rapidly. This deceleration could have a profound effect on the formation of cosmic structures, allowing gravity to exert its influence for a longer period of time before the expansion of space pushes matter apart. Over time, this would likely result in the creation of larger and more numerous cosmic structures. Superclusters of galaxies could emerge on a scale far greater than anything we currently observe. In such a scenario, the cosmic web, the vast interconnected network of filaments and voids that forms the very backbone of the universe's structure, would also undergo a transformation. The web might become more tightly woven, or conversely, it could stretch out, creating a looser structure altogether. The very fabric of the cosmos, from the smallest galactic clumps to the largest superclusters, would be reshaped by these altered forces, ultimately changing the large-scale architecture of the universe itself. These changes would ripple through every aspect of cosmic evolution. The birth and growth of galaxies would follow entirely different patterns. The distribution of matter throughout the universe would be rearranged, potentially leading to entirely new configurations. If we were able to observe this altered universe, the night sky from any hypothetical planet might look vastly different from what we see today. Depending on the specific parameters of this new cosmos, the abundance of visible stars and galaxies could be either greater or lesser. The stars that light up the night could be more numerous, stretching across the heavens in formations unseen in our universe. Alternatively, they might become more sparsely distributed, leaving behind vast expanses of dark voids between scattered constellations. Whatever the outcome, the universe as we know it would undergo a transformation of such magnitude that the view of the cosmos from any planet's surface would be unrecognizable. As humanity ventures deeper into space, the need for advanced technologies becomes more pressing. New challenges arise when considering environments that are not true vacuums, planets and moons with atmospheres like Mars or Titan. These non-vacuum environments require novel approaches and materials capable of withstanding extreme conditions. One promising area of research involves the development of advanced materials for spacecraft and spacesuits. These materials would need to resist the corrosive effects of atmospheric gases and particles. Some of these new materials might incorporate self-healing properties, which could allow them to repair themselves when damaged by harsh atmospheric conditions. Nanotechnology might be leveraged to create adaptive surfaces that respond dynamically to changes in temperature, pressure, and chemical composition, making spacecraft and suits more versatile than ever before. The next step is improving propulsion systems that function not just in the vacuum of space, but within the atmosphere of other celestial bodies. Hybrid propulsion systems are under development, blending traditional rocket technology with air-breathing capabilities. Such systems could use the atmospheric gases of planets like Mars or Venus for propulsion, potentially reducing the amount of fuel required for long-duration missions. This could extend the lifespan of spacecraft, allowing them to complete longer missions or even facilitate colonization efforts. Another avenue of research is atmospheric harvesting technologies. These systems aim to extract valuable resources, water, oxygen, or other compounds from planetary atmospheres. By tapping into local resources, these technologies would reduce the need to carry all essential supplies from Earth, enabling missions to last longer and be more self-sufficient. Such capabilities could be a game changer, especially when planning for human habitation on distant planets. As we look beyond our solar system, the challenges of interstellar travel become even more daunting. Space-based technologies would need dramatic adaptations to cope with the extreme conditions of long-term space missions. Current spacecraft are designed to navigate relatively short distances within our solar system, but interstellar travel presents an entirely different set of obstacles. Chemical rockets, which have served us well for decades, would not be sufficient for the vast distances between stars. To reach even the nearest star systems, we would need to develop new propulsion systems, such as nuclear propulsion, antimatter engines, or even theoretical concepts like warp drives, which could bend the fabric of space-time itself. These technologies would need to be perfected if humanity is ever to venture beyond the solar system. Life support systems would also need a complete overhaul. The crews aboard interstellar ships might spend decades, even centuries, traveling to distant stars, and sustaining them over such extended periods would require new advancements. Water and air recycling systems would need to be highly efficient, and radiation shielding would have to be significantly enhanced to protect against the cosmic rays and solar radiation that permeate deep space. Long-term food production and storage systems would be necessary to provide sustenance for travelers on such long journeys. Furthermore, the challenge of communication over interstellar distances would be unprecedented. Current radio systems, which rely on electromagnetic signals, experience significant delays when traveling vast distances. A communication system capable of maintaining contact across light years would need to be developed, possibly based on quantum entanglement or other principles of advanced physics. The harsh environment of space also poses significant challenges for satellite technology. Satellites orbiting Earth are subjected to intense radiation, which can damage their delicate electronic components and solar panels. To protect against these dangers, satellites must be equipped with robust shielding and backup systems to withstand the constant bombardment of cosmic rays and solar particles. Another major concern is the growing threat of space debris. Millions of pieces of man-made objects, from tiny paint flecks to defunct satellites, now orbit Earth at high speeds. Even a collision with a small fragment of debris can cause catastrophic damage to a satellite, potentially rendering it inoperable. Advanced tracking systems and the ability to perform evasive maneuvers are crucial to minimizing the risks posed by space debris. Thermal management is another key issue. Satellites in space experience extreme temperature fluctuations as they travel between sunlight and shadow, with temperatures ranging from blistering heat to freezing cold. To maintain optimal operating conditions, sophisticated cooling systems and materials with specific thermal properties are required. Without them, delicate instruments and electronics could easily malfunction or fail. In addition to temperature regulation, maintaining accurate positioning and orientation is essential for satellites to perform their functions. The effects of solar wind, atmospheric drag, and gravitational interactions with the moon and other celestial bodies can cause satellites to drift off course. This requires constant adjustments to their position using fuel and thrusters. Over time, the finite amount of fuel limits the operational lifespan of many satellites. In a universe devoid of stars, even the most fundamental navigation systems, like GPS, would face insurmountable challenges. GPS relies on precise timing provided by atomic clocks in satellites, which in turn depend on the position of fixed celestial reference points, such as stars. Without stars, maintaining an accurate orientation in space would become progressively more difficult. Over time, this could lead to significant errors in GPS systems, rendering them unreliable for navigation purposes. These errors could become more pronounced as the system ages, making it increasingly harder to track the exact position of satellites or provide precise navigation data. Without the constant celestial markers that have guided human exploration for millennia, our ability to navigate through space might face a future of uncertainty and miscalculation. In a universe without stars, the ripple effects would be profound, impacting almost every facet of human life. The first area to experience a dramatic shift would be our traditional methods of navigation. Techniques such as celestial navigation, which has guided sailors across the oceans for centuries, would become obsolete. Celestial navigation relies on the ability to sight stars in the night sky, allowing navigators to chart their course with remarkable precision. Without stars, this form of navigation, which has been integral to human exploration, would be impossible. It would not only cripple our maritime activities, but also ripple outwards, affecting modern transportation systems that depend on navigation by the stars. Our ability to map and explore the world would be hindered, and the very process of understanding our place in the cosmos would undergo an irreversible shift. In addition, the absence of stars would disrupt our understanding of Earth's position and movement within space. This could introduce significant challenges in maintaining accurate timekeeping, which is crucial to everything from global communication systems to financial markets. Precise time synchronization, which depends on astronomical observations, would become increasingly difficult. The infrastructure that underpins our modern world, from GPS to telecommunications, relies heavily on celestial bodies and the predictable patterns they exhibit. The absence of stars would force us to reimagine and redesign many of these systems, creating a ripple effect across technologies that we now take for granted. The complexities of such a transition would not only require technological innovation, but a complete rethinking of how we structure our society's most fundamental operations. However, amidst these challenges, new possibilities could emerge. Space-based manufacturing, for example, holds the potential to transform industries in ways previously thought impossible. In the microgravity environment of orbit, materials behave in radically different ways, offering opportunities to create products that would be impossible to manufacture on Earth. One particularly promising area lies in the production of ultra-pure materials, such as semiconductors and optical fibers. Without the gravitational forces that induce impurities on Earth, materials produced in space could reach levels of purity and quality previously unattainable. This would result in more efficient electronics and communications technologies, potentially revolutionizing industries that depend on these components. Moreover, space could serve as a platform for creating large, delicate structures that would collapse under their own weight on Earth. Imagine enormous solar arrays or even entire space habitats assembled in orbit, free from the constraints of gravity. These massive structures could radically change the landscape of space exploration, opening up new frontiers for human habitation and providing a sustainable source of clean energy. These innovations could also benefit life on Earth, offering solutions to energy crises and environmental challenges. The absence of gravity in space could further enhance biomedical research, offering unique conditions that allow for the perfect crystallization of proteins. These microgravity conditions could lead to breakthroughs in drug development and disease treatment, unlocking new potential for human health and longevity. As humanity ventures deeper into the exploration of space, entirely new manufacturing processes and products may emerge, changing life as we know it, not just on Earth, but throughout the cosmos. In a universe where space is no longer a vacuum, the very concept of space tourism would also undergo radical transformation. The current appeal of space tourism is largely based on the experience of weightlessness and the surreal sensation of floating in the void. In a non-vacuum environment, however, the experience would be fundamentally different. Tourists might encounter varying degrees of buoyancy or gravity, depending on the surrounding medium, which could lead to entirely new forms of movement. Instead of the free-floating sensation associated with space, travelers might find themselves gliding through a dense, gaseous, or liquid-like substance, offering a more immersive and unusual experience. The vehicles designed for such journeys would also require rethinking. Rather than spacecraft built to withstand the harsh vacuum of space, we could see the development of vessels more akin to submarines or airships. These vehicles would need to navigate through a medium, not just the vacuum of space, and would likely require entirely new propulsion systems. These could draw upon the surrounding environment, similar to how fish utilize water currents for movement. Such advancements would revolutionize our understanding of what space travel could entail, offering exciting new possibilities for exploration. Visually, space tourism in a non-vacuum environment would offer a dramatically different experience. Tourists would no longer see the stark contrast between the blackness of space and the twinkling stars. Instead, they would witness a gradual transition of colors and densities as they ascend, creating a stunning visual display as light refracts through the medium surrounding them. The celestial bodies, once seen as bright dots of light, would now appear through a haze of shifting colors and atmospheric effects, offering a breathtaking, almost dreamlike experience of the cosmos. As space exploration continues to expand, managing space debris would become a paramount concern. With more spacecraft, satellites, and other objects populating the space around Earth, keeping the orbital environment clean and navigable will require innovative solutions. Tracking systems would need to be advanced, capable of detecting even the smallest pieces of debris, which could otherwise pose a significant risk to spacecraft and satellites. These tracking systems would rely on both ground-based and space-based sensors, creating an interconnected web of monitoring to ensure the safety of space operations. Active debris removal technologies would also become essential. This could involve spacecraft equipped with nets, harpoons, or even laser systems that could push smaller pieces of debris into lower orbits, where they would eventually burn up upon re-entry into Earth's atmosphere. Electrodynamic tethers, long conductive wires, could also be attached to defunct satellites, dragging them out of orbit and into safe disposal zones. Prevention strategies would be just as important, with future spacecraft and satellites needing to be designed with built-in deorbit mechanisms to ensure they don't contribute to the growing debris problem. International cooperation would be necessary to regulate these activities, ensuring that space remains a safe and sustainable environment for all. The consequences of a universe where space is not a vacuum would extend far beyond the confines of our own planet. Our fundamental understanding of the cosmos would change forever. The vast expanses of space between stars, galaxies, and other celestial bodies would no longer be empty. Instead, these regions would be filled with some form of matter or energy, altering the way light and gravity interact across cosmic distances. The observable universe would become obscured as the intervening medium scatters, absorbs, or distorts the light from distant stars and galaxies. This would limit our ability to study the far reaches of the cosmos, making it impossible to gain insights into the structure and evolution of the universe. Additionally, the dynamics of celestial bodies would change dramatically. The drag created by the presence of a medium in space would slow down orbiting planets, stars, and galaxies, altering the fundamental forces at play within the cosmos. This would challenge our understanding of gravity and the processes that govern the formation of cosmic structures, from solar systems to galaxy clusters. The presence of a medium would add new layers of complexity to our understanding of celestial mechanics, forcing scientists to revise theories and models that have long been considered foundational to our comprehension of the universe. The implications of such a dramatic change would be far-reaching, reshaping the very fabric of our understanding of space, time, and the cosmos itself. Moreover, the propagation of electromagnetic waves and gravitational waves through a non-vacuum space would undergo significant alteration, deeply affecting our capacity to detect and study cosmic phenomena such as black holes, neutron stars, and the cosmic microwave background. This disruption would have profound implications for the theories of physics that shape our understanding of the universe. Our grasp of the fundamental laws that govern reality, and even the very history of the cosmos since the Big Bang, could be dramatically reshaped. If other universes exist, the revelation would ignite a series of profound debates that would reverberate not only through the scientific community, but also within the realm of philosophy. The discovery would prompt a reevaluation of what we know about the nature of reality itself. Philosophers and scientists alike would wrestle with questions of cosmic significance. Are the laws of physics the same in all universes, or do different universes operate under entirely unique sets of rules? This issue could fundamentally challenge our existing notions of constants in physics and the very fabric of existence. If multiple universes exist, it could lead to an entirely new understanding of infinity. The idea of infinite universes implies that every conceivable reality might exist somewhere in the vastness of the multiverse. This touches upon the philosophical idea of modal realism, suggesting that all possible worlds are just as real as our own. Such a discovery would force humanity to reconsider its place in the cosmos and to question whether our individual actions truly have meaning in a multiverse filled with endless possibilities. In addition, the nature of consciousness and its relationship with the physical universe would come under intense scrutiny. If our consciousness is uniquely tied to the specific conditions of our universe, could there be alternative forms of awareness in other universes with different laws of physics? This inquiry overlaps with the hard problem of consciousness, questioning whether the mind is fundamentally distinct from matter. These philosophical concerns are not merely abstract. They would have profound implications for how we think about existence, intelligence, and life itself. Ethical questions would also arise from the possibility of interacting with or influencing other universes. If we had the ability to affect realities beyond our own, what would our moral obligations be? Would we have a duty to intervene in universes where suffering is more pronounced? Or would a stance of non-interference be the most ethical choice? The answers to these questions would challenge the very foundations of our ethical frameworks, expanding them far beyond the confines of our own cosmic neighborhood. This revelation would alter humanity's perception of its own significance in the grand scheme of the universe. For centuries, humans have grappled with questions of our place in the cosmos. The discovery that our universe is just one of many would radically expand our perspective, leading us to reconsider our uniqueness and sense of purpose. It would invite us to reflect not only on our role within our own universe, but also within a potentially infinite and multifaceted multiverse. This would mark a profound shift in how we understand our place in existence. Such a breakthrough would also ignite a revolution in scientific thought. The discovery of other universes would provide unprecedented opportunities to explore fundamental questions regarding the nature of reality, the origins of our universe, and the governing laws of physics. Scientists would need to devise entirely new models and theories to account for the interactions between multiple universes and to identify any universal principles that might apply across the multiverse. This intellectual challenge would open up new frontiers for inquiry, pushing our understanding of the cosmos into uncharted territory. Moreover, this newfound knowledge would likely provoke a surge in both philosophical and existential debates. Questions about free will, determinism, and the existence of alternate versions of ourselves would transition from theoretical curiosities to real issues of cosmic consequence. The awareness that different versions of reality exist, where different choices and decisions were made, would fundamentally alter how we view our own choices and their potential consequences. While such a discovery might initially diminish our sense of importance in the vastness of the multiverse, it could also inspire a renewed sense of wonder and possibility. The idea that our universe is only one among an infinite number could lead to a deeper appreciation for our unique existence. It could galvanize humanity to explore further and seek a deeper understanding of our place in the vast, multi-layered reality that surrounds us. Rather than feeling insignificant, we might be motivated to delve into the mysteries of the cosmos with a heightened sense of purpose. As humanity pushes further into space, it will inevitably encounter a host of new ethical dilemmas. One of the most pressing concerns is the potential contamination of extraterrestrial environments with Earth-based microorganisms. Such contamination could irreversibly alter alien ecosystems, making it difficult to distinguish between native life and human influence. The search for extraterrestrial life could become infinitely more complex if we introduce foreign life forms into these environments, potentially complicating our scientific pursuits. At the same time, the exploitation of space resources raises serious ethical questions. As technology advances and we begin to mine asteroids or establish colonies on other planets, disputes over the ownership and use of these resources could arise. Which nations or corporations have the right to claim and extract these materials? This could lead to conflicts that mirror the territorial disputes of our own planet, but on a cosmic scale, potentially pitting the interests of Earth's governments against those of newly formed space colonies or corporations seeking profit. The long-term effects of space travel on human health present another ethical challenge. The harsh conditions of space, such as extended periods in microgravity and exposure to cosmic radiation, can have serious effects on the human body. These conditions can lead to bone density loss, muscle atrophy, and an increased risk of cancer. As we continue to send astronauts on longer missions, we must confront the ethical responsibility of asking individuals to endure these risks for the advancement of human knowledge. Finally, as we consider the prospect of establishing permanent settlements on other worlds, we must address the ethical implications of creating new societies beyond Earth. What governance structures will we put in place? How will we protect human rights in space colonies? Will conflicts arise between the inhabitants of these new worlds and Earth-based authorities who may seek to maintain control over them? These questions highlight the complex ethical challenges humanity will face as we expand beyond our home planet and begin to take our place in the broader universe. Our quest for meaning in the cosmos is inextricably linked to our understanding of the vastness and complexity of the universe. As we uncover the intricate workings of celestial bodies and the fundamental laws of physics, we are constantly reminded of how much we have yet to learn. The sheer scale of the universe, with its billions of galaxies and trillions of stars, offers both a humbling perspective and exciting possibilities. This vastness raises profound questions about the potential for life and intelligence elsewhere, encouraging us to look deeper into space and explore further than ever before. This search for knowledge is not merely an intellectual pursuit. It touches on the very nature of human existence and the purpose of life. As we venture further into the unknown, the quest for understanding propels us to reflect on our place in the universe, on our role in the grand, unfolding story of existence. With every new discovery, we are forced to confront not only the mysteries of the cosmos, but also the mystery of our own existence and the meaning we derive from it. This cosmic journey, driven by our curiosity and thirst for knowledge, will continue to shape our future in ways we cannot yet fully comprehend. The exploration of cosmology has continually challenged the boundaries of human understanding, revealing unexpected and intricate connections between the extremely large and the infinitesimally small. From the behavior of subatomic particles to the formation of vast galactic superclusters, each new discovery contributes another piece to the grand cosmic puzzle. These revelations suggest a profound interconnectedness that spans the entire universe, implying that our search for meaning may not solely be confined to distant stars, but instead may lie in understanding our relationship with the very fabric of the universe itself. As we expand our knowledge of the cosmos, it becomes clear that the pursuit of meaning transcends the scope of individual lives. It is not just about our place in the world. It is about how we as a species fit into the broader narrative of an ever-evolving universe. The cosmos beckons us to consider our collective journey, pushing us to think beyond our immediate surroundings and engage with the vast, dynamic expanse that stretches across space and time. This journey challenges us to think in broader terms, not just as individuals, but as a species bound together by the same cosmic forces. One of the most profound aspects of modern cosmology is how it challenges our understanding of space, time, and even infinity itself. The expansion of the universe, a concept that has become central to current scientific models, forces us to reconsider what infinity truly means. If the universe continues to expand indefinitely, as current theories suggest, we must confront the possibility of an eternal cosmos, one where galaxies drift further and further apart, eventually isolated to the point where light from one can never reach another. This scenario, often referred to as the Big Freeze, presents a chilling view of eternity, in which connection and interaction across vast distances become impossible. This vision of an infinite and eternally expanding universe forces us to rethink the concept of infinity itself. Is infinity a simple concept, or does it take on new dimensions when we consider the possibility of multiple universes or dimensions? If our expanding universe is but one of many, the scale of infinity grows exponentially. Moreover, if time itself began with the Big Bang, we are left to wonder, does eternity truly have a beginning, or does it stretch infinitely in both directions? These cosmic implications extend far beyond the realm of physics and mathematics. They inevitably raise profound philosophical and existential questions about the nature of existence itself. Our place in the universe, once thought to be the center of creation, now appears more fleeting, more humble. The universe is no longer a simple finite object. It is an ever-expanding mystery, one that continually defies our attempts to understand its scope and purpose. As we grapple with the mind-boggling scale of the universe, we are reminded of the limits of human perception. No matter how advanced our technology becomes, there will always be mysteries beyond our reach, waiting to be discovered. The expansion of the universe presents new challenges, not just for physics, but for how we perceive ourselves in relation to the cosmos. It serves as a constant reminder that the universe is not something to be understood in terms of individual moments or lifetimes, but as a vast, ever-changing entity that stretches across the eons. At the intersection of science and spirituality, the discoveries of modern cosmology have led to a re-evaluation of many religious and spiritual beliefs. As our understanding of the universe deepens, some find their faith strengthened by the sheer awe-inspiring complexity of creation. The intricate design of the cosmos, with its vast galaxies, black holes, and unfathomable distances, inspires awe and a sense of the divine. Others, however, struggle to reconcile the new discoveries with traditional beliefs, particularly when they conflict with long-held views on the age of the universe or the uniqueness of Earth and humanity. For example, the concept of a universe that is billions of years old stands in direct contrast to literal interpretations of religious texts that suggest a much younger cosmos. The notion of multiple universes or the potential for extraterrestrial life raises questions about the uniqueness of Earth and humanity's role in creation. Yet many religious traditions have found ways to integrate scientific discoveries into their worldviews. Some see the complexity and beauty revealed by science as evidence of a higher power, while others interpret religious texts in a more metaphorical way, harmonizing faith with the findings of modern science. This dialogue between science and religion has led to the emergence of new theological perspectives, ones that seek to bridge the gap between the two. These perspectives do not necessarily resolve all conflicts, but they open up avenues for deeper exploration and greater understanding. The impact of scientific knowledge on religious and spiritual perspectives is far from uniform, varying significantly between individuals and communities. What remains consistent, however, is that the conversation it sparks is profound and transformative, encouraging a deeper exploration of both scientific truths and spiritual mysteries. In recent years, alternative theories in physics have challenged long-standing assumptions about the nature of space and the universe itself. Traditional models of physics have been built on the assumption of a vacuum universe, but this may not be an accurate representation of reality. Some theorists propose that space is filled with an undetected substance or field, an idea that has the potential to revolutionize our understanding of space-time. One such theory posits the existence of a quantum foam at the smallest scales of space, where space-time itself is not smooth but fluctuates constantly. This foam could interact with matter and energy in ways that our current models do not account for, potentially offering new explanations for cosmic phenomena such as dark energy. Another compelling idea is that the universe might be permeated by a cosmic fluid, an all-encompassing substance with properties similar to a superfluid. Such a medium could flow without losing energy and influence the expansion of the universe, providing new insights into the behavior of galaxies and the ultimate fate of the cosmos. These theories, though speculative, are challenging our current understanding and prompting new avenues of research. If proven, they could fundamentally alter our conception of the universe and our place within it. Among the most ambitious of these theories is the idea that our universe might exist within a higher dimensional space, a concept known as brane cosmology. According to this theory, gravity could be leaking into extra dimensions beyond our own, which may help explain why gravity is weaker than the other fundamental forces. It could also provide alternative explanations for the mysterious phenomena known as dark matter and dark energy, which have long eluded explanation. As these new theories challenge traditional models, they open up new frontiers in physics and cosmology. By investigating the potential existence of a quantum foam, a cosmic fluid, or the possibility of multiple dimensions, scientists are attempting to build a more complete and accurate description of the universe. Such breakthroughs could revolutionize not only our understanding of the cosmos, but also the very laws of physics that govern its behavior. String theory, a framework designed to unify the fundamental forces of nature, is also being scrutinized in light of these new ideas. Traditionally, string theory has focused on a vacuum universe, one that is empty of matter. To accommodate a universe filled with matter, theorists would need to modify string theory, particularly in relation to the extra dimensions it proposes. These additional dimensions, which are usually thought to be compactified or curled up, might need to be reshaped or resized to reflect the presence of matter. The geometry of these extra dimensions could be influenced by the distribution and density of matter in the observable universe, further complicating our understanding of space and time. These developments in theoretical physics and cosmology have the potential to radically alter our view of the universe. What once seemed like abstract and speculative ideas may soon lead to new discoveries that challenge everything we thought we knew. As we continue to explore the deepest reaches of the cosmos, we may find that the answers we seek are even more complex and awe-inspiring than we ever imagined. String theory, at its core, seeks to provide a deeper understanding of the universe by addressing one of the most profound mysteries in physics: how the fundamental building blocks of matter and forces interact at the most basic level. A crucial aspect that string theory must contend with is how the presence of matter influences the vibrational patterns of strings. In the framework of string theory, these vibrations are not just a mere theoretical construct. They are thought to give rise to the myriad particles and forces that compose the universe. However, the environment in which these vibrations occur plays a significant role. The presence of matter, energy, and other cosmic elements can potentially dampen or alter these vibrational patterns. This would lead to new predictions about the behavior of particles and their interactions, especially in a matter-filled space. The complexity of these interactions could have far-reaching implications, altering the way we understand fundamental particle dynamics. Furthermore, string theorists must reconcile their models with the large-scale structures observed throughout the universe. Galaxies, galaxy clusters, and the vast voids between them represent the large-scale architecture of the cosmos, and string theory must integrate these observations into its framework. The challenge here is monumental. To do so, string theory would need to incorporate key concepts from cosmology and astrophysics, weaving them seamlessly into its theoretical structure. This integration could yield revolutionary insights into dark matter and dark energy, two enigmatic substances that seem to dominate the universe's composition yet remain invisible and largely undetectable by conventional methods. As scientists continue to probe deeper into the mysteries of the universe, the possibility of uncovering new fundamental forces beyond the four we already know — gravity, electromagnetism, the strong nuclear force, and the weak nuclear force — becomes increasingly tantalizing. One particularly intriguing candidate for this elusive fifth force is a force that could explain both dark matter and dark energy, which together make up roughly 95% of the universe's content. The existence of such a force could transform our understanding of the cosmos. Some researchers suggest that this force might be mediated by hypothetical particles called simons. These particles, if they exist, could help explain the accelerating expansion of the universe, a phenomenon attributed to dark energy. Interestingly, this proposed force would be extraordinarily weak in dense environments, such as within our solar system, yet it would become increasingly significant on larger cosmic scales, potentially offering a reason for why it has not been detected in laboratory experiments. Another fascinating possibility arises from the notion that dark matter itself might exert an undiscovered force on ordinary matter. Although dark matter has never been directly observed, its presence is inferred from its gravitational effects on galaxies and galaxy clusters. Some theories propose that dark matter could interact with normal matter in ways we have not yet been able to detect. These interactions might involve particles or fields that become evident only under extreme conditions, such as in the dense environments of neutron stars or near the event horizons of black holes. These potential interactions could reveal an entirely new dimension to particle physics, one that challenges the very foundation of how we understand matter and energy. Quantum gravity, a theory aimed at reconciling the principles of general relativity with those of quantum mechanics, also holds the potential to unveil new forces or modify our current understanding of known forces. This theory is driven by the idea that gravity, like the other forces of nature, may exhibit quantum properties that manifest only at extremely small scales or at high energies. By exploring these aspects, scientists hope to uncover fundamental interactions that were previously invisible, reshaping the way we perceive the very fabric of space-time. The standard model of particle physics, which remains the cornerstone of our current understanding, has been immensely successful in describing the fundamental particles and forces of the universe. However, as with all scientific models, it is subject to change. One possible shift involves the discovery of new particles that lie beyond the current model's scope. Dark matter is a prime candidate in this regard, as scientists continue to search for particles that could account for its mysterious presence. Dark matter constitutes a significant portion of the universe's mass, yet its properties remain elusive. If new particles were discovered, they could provide the missing pieces of the puzzle, forcing a major reevaluation of the standard model. Another way in which the standard model might evolve is through the unification of forces. Currently, the standard model successfully describes 3 of the 4 known fundamental forces: the strong nuclear force, the weak nuclear force, and electromagnetism. Gravity, however, remains an outlier. A major goal in physics is to find a unified theory that brings all 4 forces under a single framework. Such a breakthrough would not only dramatically alter our current understanding, but would also open the door to new, unforeseen insights about the nature of the universe. The standard model could also require significant revisions in response to new experimental findings. For instance, if neutrinos were found to have more mass than previously thought, or if protons were discovered to decay, the current model would need to be adjusted to account for these unexpected properties. Moreover, research into antimatter, the opposite counterpart of ordinary matter, may lead to further revisions. Antimatter's scarcity in the observable universe has long been a mystery. Yet, recent advancements in particle physics and cosmology are shedding light on its properties, and these findings could force a reevaluation of the early universe's history and the processes that led to the dominance of matter over antimatter. Perhaps the most profound challenge to the standard model comes from the discovery of the Higgs boson in 2012. While the Higgs boson's discovery confirmed the mechanism by which other particles acquire mass, it also opened new avenues for investigation. As scientists delve deeper into understanding the Higgs field and its interactions, it is possible that new aspects of this particle will be revealed, requiring adjustments to our existing theories. In the ongoing quest to understand the universe, alternative theories to dark matter and dark energy are also gaining traction. Modified gravity theories, for example, propose that our current understanding of gravity might be incomplete. These theories suggest that gravity behaves differently on cosmic scales, offering alternative explanations for phenomena such as the rotation of galaxies and the accelerated expansion of the universe, without invoking dark matter or dark energy. Emergent gravity is another promising alternative. According to this idea, gravity may not be a fundamental force in and of itself, but may emerge from the quantum structure of space-time. If this theory proves to be correct, it could provide an explanation for some of the cosmic phenomena currently attributed to dark matter and dark energy. In this framework, the force of gravity could be a secondary effect, arising from deeper, more fundamental interactions within the quantum realm. In addition to these gravitational theories, some researchers are investigating the potential role of exotic particles or fields that could mimic the effects of dark matter and dark energy. These include ultralight particles, scalar fields, and even hidden dimensions, concepts that challenge the boundaries of conventional physics. Such particles and fields might interact with the observable universe in subtle ways, giving rise to the cosmic phenomena we observe today. Lastly, there is a growing body of work that suggests the existence of a multiverse, an ensemble of multiple universes beyond our own. In this scenario, the influence of other universes could explain the strange behavior of dark energy. If our universe is merely one of many, the effects of other unseen universes could be shaping the properties of our own. While the idea of a multiverse is highly speculative, it represents an exciting frontier in cosmology that could completely transform our understanding of reality. As we continue to explore the universe's deepest mysteries, the implications of these ideas could prove to be paradigm-shifting. Every new discovery brings us one step closer to understanding the true nature of the cosmos. As scientists push the boundaries of our knowledge, New findings in fields like antimatter, and dark energy could revolutionize our understanding of physics and lead to breakthroughs that we can only begin to imagine. The exploration of antimatter has the potential to unlock entirely new technological frontiers, ones that could revolutionize space exploration and medical research. Imagine, for instance, antimatter-based propulsion systems that could vastly enhance the efficiency of spacecraft, enabling humanity to venture further into the cosmos than ever before. Alongside this, advanced medical imaging techniques grounded in antimatter research could lead to breakthroughs in how we diagnose and treat complex health conditions, pushing the boundaries of modern medicine. Such advancements would not only significantly expand our scientific knowledge, but also spark new questions, igniting fresh avenues for investigation. As we delve deeper into the mysteries of antimatter, we find ourselves piecing together a crucial part of the cosmic puzzle, one that could alter our entire understanding of the universe. At the heart of this unfolding journey lies the concept of non-vacuum space, an idea that challenges everything we thought we knew about particle physics and quantum mechanics. Our understanding of what constitutes empty space may soon be overturned, and scientists are already theorizing the existence of entirely new subatomic particles that could explain this strange phenomenon. One possible candidate for this new class of particles is the so-called chameleon particle. These particles would possess the ability to alter their mass and properties based on their environment. In the vacuum of space, they could be incredibly light, but in denser environments, they could become much heavier. This could explain the apparent emptiness of space while simultaneously accounting for its non-vacuum nature, suggesting that what we perceive as nothing may, in fact, be teeming with unseen forces. Further complicating the picture, scientists have proposed the existence of additional force-carrying particles that have yet to be detected. These would function in a manner similar to known force carriers like photons, which mediate electromagnetism, or gluons, which govern the strong nuclear force. However, these new force carriers would have properties that allow them to permeate space without being easily detectable by our current instruments. Such particles might interact only weakly with ordinary matter, making their detection a daunting challenge. Another intriguing possibility is the concept of sterile neutrinos, hypothetical particles that do not interact via the weak nuclear force. These particles could be tied to dark matter, and their elusive nature makes them even harder to detect. The ongoing search for these particles is pushing the limits of our scientific capabilities. With the aid of advanced particle accelerators and increasingly sensitive detectors, the day may come when we finally uncover these hidden aspects of reality, offering insights that could radically transform our understanding of the universe. But these discoveries also come with significant challenges, particularly for the field of astronomy. If the universe were filled with a dense abundance of matter, optical astronomy would be rendered nearly useless. The sheer density of matter would create an opaque environment, one in which light could not easily penetrate. As light travels through space, it would constantly scatter, change direction, or even be absorbed entirely by the particles in its path. This phenomenon would be akin to trying to see through a thick fog or smoke, but on a cosmic scale. The result would be a dramatic reduction in the observable universe, limiting our ability to study distant stars, galaxies, and other celestial bodies. Only the closest and brightest objects would remain visible, severely restricting our understanding of the broader cosmic structure and the evolution of the universe. To adapt to these conditions, astronomers would have to explore other methods of observation, such as radio astronomy or gravitational wave detection. These alternative techniques could potentially penetrate the dense matter more effectively, allowing us to probe the cosmos beyond the reach of traditional optical observation. However, even these methods are not without their own obstacles. As humanity expands its presence in space, the number of satellites and space debris in Earth's orbit will increase, leading to more interference in radio astronomy. The signals from distant cosmic sources could become increasingly difficult to detect due to the growing radio pollution from human activity. To address this, scientists may need to develop more sophisticated filtering techniques or relocate radio telescopes to quieter, more remote environments, such as the far side of the moon, where interference from Earth would be minimized. As space exploration progresses, radio emissions from human settlements on other celestial bodies could add further complications. Lunar bases or Martian colonies would generate their own radio noise, potentially drowning out faint signals from the far reaches of the universe. To mitigate this, careful planning would be required to maintain radio quiet zones, ensuring that these areas remain free of interference to allow for the most sensitive astronomical observations. This coordination would be vital as humanity balances its space colonization efforts with the need for continued scientific discovery. Simultaneously, the development of more powerful and sensitive radio telescopes presents new challenges. These instruments would be capable of detecting a much wider range of radio signals, leading to a deluge of data that would require advanced processing techniques and artificial intelligence to analyze effectively. Scientists would need to develop innovative methods to sift through this overwhelming volume of information, identifying the most significant astronomical phenomena amid the noise. Furthermore, as our understanding of the universe continues to grow, radio astronomers would face the increasing challenge of detecting ever fainter signals from distant cosmic sources. Pushing the limits of technology, this may require the development of new observational techniques, such as large arrays of telescopes spread across multiple planets, or even extending into deep space. Such expansive networks would be necessary to achieve the sensitivity and resolution required to make groundbreaking discoveries about the nature of the universe. Our observations of distant galaxies would undergo profound changes if we altered our vantage point or the fundamental properties of the universe itself. The light emitted by distant galaxies takes billions of years to reach us, meaning that when we observe these far-off cosmic structures, we are essentially looking back in time. If we were able to instantly transport ourselves to a different location in the cosmos, our view of these galaxies would shift in dramatic ways. We might see them from new angles, revealing previously hidden features, or conversely, some familiar aspects might become obscured. Galaxies that once appeared distant from Earth might suddenly seem much closer, while others could retreat further into the cosmic background. The expansion of the universe plays a key role in shaping these observations. As the universe continues to expand, light from distant galaxies is stretched, a phenomenon known as redshift. If the rate of expansion were to change, the degree of redshift we observe would also shift, potentially altering the apparent distances to galaxies and even making some appear closer or farther away than they actually are. This dynamic process emphasizes the fluid nature of our observations and the constantly evolving understanding of the universe around us. Changes in the composition of the intergalactic medium would have profound implications on how we observe and understand distant galaxies. The amount and type of gas and dust present between us and these far-off objects can either obscure or reveal critical details about their structure and composition. This would not only alter our perception of individual galaxies, but could dramatically shift our understanding of galactic evolution and the early stages of the universe itself. The intergalactic medium acts as a cosmic veil, sometimes letting light pass through it with little distortion, and other times hiding the very features we seek to explore. Variations in its composition could thus bring about significant adjustments in the way we perceive the universe's vast, intricate tapestry. As technology progresses, our ability to detect and analyze exoplanets will undergo radical transformation. Future space telescopes armed with more sensitive instruments would allow us to observe planets orbiting distant stars with unprecedented detail. Smaller, Earth-like planets that might have been previously undetectable due to their faint signals could come into clear view. These advanced tools will also allow us to study the atmospheres of these exoplanets in much greater detail, possibly uncovering signs of life or conditions suitable for habitability. Such breakthroughs would not only satisfy our inherent curiosity about distant worlds, but could also take us one step closer to answering the age-old question, are we alone in the universe? Ground-based observatories would play an equally pivotal role in this revolution. With larger, more sophisticated telescopes featuring adaptive optic systems, we would gain clearer and more detailed views of distant solar systems. This would allow us to directly image exoplanets and study their characteristics, such as their surface conditions and atmospheric compositions. These innovations in observational power would be paired with improvements in data analysis techniques. Artificial intelligence and advanced algorithms would assist scientists in sifting through massive amounts of data, enabling them to identify potential exoplanets more quickly and accurately than ever before. The sheer volume of data that modern telescopes and observatories gather would require cutting-edge computational power to process and interpret, but with these advancements, our ability to detect new worlds would expand exponentially. In addition to current methods such as transit photometry and radial velocity measurements, new detection techniques would greatly enhance our capacity to discover exoplanets. For instance, advancements in astrometry, the precise measurement of star positions, would allow us to detect even the most subtle movements of stars caused by orbiting planets. This could prove especially useful for detecting planets that orbit at greater distances from their host stars. As our capabilities in astrometry and other detection methods improve, we would not only increase our understanding of the diversity of planets in the universe, but also refine our search for potentially habitable ones. This knowledge could be crucial as we seek to find environments that could support life beyond Earth. Gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity, would also undergo significant changes in a universe with varying fundamental constants. In our current universe, massive objects such as galaxies and galaxy clusters bend light from distant sources, creating natural cosmic magnifying glasses. However, if fundamental constants like gravity or the speed of light were altered, this effect would be dramatically different. If gravity were stronger, gravitational lensing would become more pronounced, with light bending more sharply around massive cosmic structures. This could potentially reveal previously hidden objects and offer clearer insights into the universe's early stages. On the other hand, weaker gravity would reduce the lensing effect, making it harder to detect distant objects in this way. Changes in the speed of light would also alter the behavior of gravitational lensing. A slower speed of light would enhance the lensing effect, as light would linger longer in the warped space around massive objects. This could result in more extreme distortions and multiple images of distant galaxies. Conversely, if light were faster, the lensing effects would be weaker, potentially limiting our ability to use this phenomenon to probe the universe. These shifts in gravitational lensing could have far-reaching consequences for cosmology, requiring astronomers to rethink how they study dark matter, measure cosmic distances, and even detect exoplanets. Such changes would fundamentally reshape our understanding of the cosmos and challenge our place within it. With advancements in technology, we are on the cusp of uncovering a host of new celestial wonders that have long remained elusive. One of the most exciting prospects involves the potential observation of primordial black holes, objects theorized to have formed in the very early universe. These enigmatic objects could provide invaluable insights into the nature of dark matter and the conditions that prevailed shortly after the Big Bang. The study of these primordial black holes would offer a direct glimpse into the most ancient epochs of the cosmos. Another tantalizing prospect is the potential detection of exomoons, moons that orbit distant exoplanets. Although we have already identified thousands of exoplanets, confirming the existence of moons around them has proven to be a much more challenging task. With enhanced observational tools and detection methods, we may soon be able to reveal these celestial companions. This discovery would not only expand our understanding of planetary system formation, but could also increase our awareness of the conditions necessary for life beyond Earth. Meanwhile, the emerging field of gravitational wave astronomy is opening up entirely new avenues for exploration. This revolutionary technology allows us to hear the ripples in space-time caused by catastrophic cosmic events. The ability to detect and study these waves could allow us to observe exotic phenomena like cosmic strings, hypothetical one-dimensional defects in the fabric of space-time. If these strings exist, they could provide critical insights into the nature of the early universe and fundamental physics. Furthermore, future advancements in observational technology might allow us to directly image the event horizons of supermassive black holes in distant galaxies. Building upon the success of the Event Horizon Telescope, future observations could reveal the dynamic behavior of these colossal objects, shedding light on the extreme physics at play in the most energetic regions of our universe. Such revelations would deepen our understanding of the universe's most mysterious and enigmatic entities. However, studying the early universe would become significantly more challenging without access to essential observational evidence like the cosmic microwave background radiation. This ancient light, which has been traveling through space for billions of years, serves as our primary window into the conditions of the infant universe. Without this crucial data, our understanding of the Big Bang and the formation of cosmic structures would be severely limited. The absence of the cosmic microwave background would hamper our ability to test and refine cosmological models, forcing scientists to rely more heavily on indirect methods and theoretical models. Additionally, without access to distant galaxies and quasars, cosmic time capsules that allow us to peer billions of years into the past, our knowledge of galactic evolution and the expansion history of the universe would be profoundly constrained. These objects provide critical information about the distribution of matter and energy in the early universe, and their absence would severely hinder our ability to test key cosmological theories. The study of primordial elements, particularly the abundance of hydrogen and helium formed shortly after the Big Bang, would also be compromised. These elements are fundamental to understanding the conditions that existed in the universe's early stages. Without direct observation of these elements in ancient, distant objects, our understanding of nucleosynthesis and the early stages of cosmic chemistry would remain incomplete. Many fundamental questions about our cosmic origins, such as the nature of inflation, dark matter, and dark energy, would remain unsolved. This lack of observational evidence could significantly slow the pace of progress in unraveling the mysteries of the universe's earliest moments. In a universe where space is not a vacuum, interstellar travel would face entirely new challenges and possibilities. The presence of matter between stars would alter our understanding of space exploration and the technologies required for long-distance travel. In a vacuum-based system, spacecraft can maintain their velocity with minimal energy input once they reach their desired speed. However, in an environment filled with interstellar matter, these assumptions would no longer hold true, demanding entirely new propulsion systems and technologies to navigate and traverse vast distances between stars. The future of interstellar exploration would thus be shaped by the presence of matter in space, prompting a re-evaluation of how we approach one of humanity's greatest aspirations, reaching the stars. However, in a non-vacuum environment, constant propulsion would be absolutely essential to counteract the drag created by the interstellar medium. This medium, which exists between the stars, would continuously slow down spacecraft, making it necessary to develop engines far more powerful and efficient than anything we currently possess. The very nature of this medium would be a crucial factor in determining the kinds of propulsion systems we could develop. If the medium were gaseous, there might be a way to harness it for propulsion, much like how aircraft rely on Earth's atmosphere for lift and thrust. This opens up the possibility of utilizing this medium for fuel, potentially leading to much more efficient methods of travel across the cosmos. On the flip side, the presence of this interstellar medium would make navigation significantly more complex. The matter between stars could severely affect the transmission of electromagnetic signals, disrupting the communication and guidance systems that we currently use to navigate spacecraft. This means new and highly advanced systems would need to be developed to account for these distortions in signal propagation and to ensure that spacecraft can still be navigated accurately over such immense distances. As we push the boundaries of space exploration, several promising propulsion technologies could revolutionize our approach. One of the most promising technologies is ion drives. These systems use electrical fields to accelerate charged particles, providing efficient long-term thrust that is ideal for deep space missions. Some spacecraft have already successfully utilized ion propulsion, and this technology could be scaled up for use on much larger vessels. Another exciting possibility lies in antimatter propulsion. By harnessing the extraordinary energy released when matter and antimatter collide and annihilate each other, spacecraft could potentially achieve speeds that far exceed what is currently achievable with chemical rockets. However, significant challenges remain, particularly in the production and safe storage of antimatter, before it can be used as a viable propulsion method. Nuclear propulsion, whether based on fission or fusion, also holds immense promise. These systems could provide the power necessary for rapid interplanetary travel. In a nuclear fission system, the products of fission reactions are directed to generate thrust, while in fusion-based propulsion, the energy from nuclear fusion reactions could propel spacecraft to unprecedented speeds. For example, travel times to Mars could be reduced from months to weeks. Then there are more theoretical concepts, such as the Alcubierre warp drive, which posits that it may be possible to manipulate spacetime itself to allow for faster-than-light travel. Though purely speculative at this stage, such technologies could one day make interstellar exploration a reality, opening up the vast reaches of space to human exploration. Yet, the concept of generation ships, spacecraft designed to sustain human life for centuries or even millennia during interstellar travel, faces a multitude of challenges, especially in the context of an ever-expanding universe. These massive vessels would need to accommodate the growing distances between stars and galaxies as the universe continues to expand. A journey that might have been calculated to take 1,000 years at the outset of the voyage could, in theory, stretch on for much longer as the universe's expansion accelerates. This increasing travel time would place even greater demands on the life support systems, resource management, and social structures required to maintain a stable population over multiple generations. The expanding universe would also have a significant impact on navigation and destination planning for these ships. Stars and galaxies that were initially targeted as potential new homes for humanity might drift farther away or become unreachable as the universe continues to expand. Generation ships would need propulsion systems so advanced that they could adjust their course and speed to account for this cosmic expansion. Moreover, crews aboard these vessels would have to be prepared for the possibility that the original destination might no longer be viable upon arrival. They would need the flexibility to adapt their plans and potentially seek out new habitable worlds in an increasingly uncertain and ever-changing cosmic landscape. This uncertainty would add another layer of complexity to the already daunting challenge of multi-generational space travel. In a universe expanding at an accelerating rate, long-distance space communication would present an entirely new set of obstacles. As spacecraft venture further into the cosmos, the vast distances between them and Earth result in significant delays in signal transmission. For example, sending a signal to a probe on Mars can take anywhere from 3 to 22 minutes, depending on the relative positions of the planets. This means real-time communication is impossible, and mission planners must carefully account for these delays when operating spacecraft. The immense distances also cause signal degradation, as radio waves spread out and lose strength as they travel. By the time a signal reaches Earth from a spacecraft thousands or even millions of light years away, it can be so faint that it requires large, highly sensitive receiving antennas to detect and interpret the message. The further a probe travels, the more powerful its transmitter needs to be, and the larger the receiving dishes on Earth must become to maintain clear communication. In addition to the vast distances involved, space itself presents other barriers to communication. Interference from cosmic radiation, solar activity, and even other celestial bodies can distort or completely block signals. Moreover, when a spacecraft passes behind a planet or enters a planetary atmosphere, communication can be temporarily lost. This phenomenon, known as occultation, means that mission planners must anticipate and work around such interruptions. To complicate matters further, spacecraft often rely on limited power sources such as solar panels or radioisotope thermoelectric generators. As missions extend further from the sun, less solar energy is available, forcing mission planners to make difficult trade-offs between powering communication systems and other critical spacecraft functions. These challenges have driven ongoing research into more efficient communication technologies, including optical communication using lasers. Laser-based communication systems could potentially transmit data at much higher rates over vast interplanetary distances, providing a promising alternative to traditional radio waves. Another highly speculative area of interest is the concept of wormholes and space warps. These theoretical structures, if they exist, could provide shortcuts through space-time, drastically reducing travel times between distant points in the universe. However, as the universe continues to expand, these potential shortcuts would be severely impacted. The stretching of space could distort or even collapse wormholes, making them unstable or rendering them unusable. Similarly, space warps, which are distortions in the fabric of space-time itself, might be amplified or diminished by cosmic expansion, affecting their potential to facilitate faster-than-light travel or communication. The increasing distance between the entry and exit points of a wormhole could make it more difficult or even impossible for anything to pass through. These effects would likely limit the usefulness of such technologies for future interstellar travel. If humanity were to venture into a universe filled with matter, we would face an entirely new set of dangers. The most immediate risk would be the constant threat of collisions. Unlike the relatively empty space we know today, a matter-filled universe would be densely packed with particles, dust, and even larger objects. Spacecraft would require extraordinarily robust shielding to withstand the relentless bombardment from high-speed particles. Additionally, the increased presence of matter would lead to higher levels of cosmic radiation, which could pose a significant hazard to both equipment and human health. Advanced protection systems would be needed to shield spacecraft and their occupants from this radiation. Navigation through such a crowded universe would also be incredibly challenging. Traditional methods of plotting courses through space would become nearly impossible, as the gravitational influences of countless nearby objects would constantly alter the spacecraft's trajectory. New, highly adaptive navigation systems would need to be developed to navigate safely through such a densely packed cosmic environment. Moreover, the abundance of matter would drastically affect the propagation of electromagnetic signals. Communication between spacecraft and with Earth would be severely hampered, as radio waves and other signals would be scattered and absorbed by the surrounding particles and dust. This would lead to dangerous isolation for space travelers who would need new communication technologies to overcome these obstacles. Finally, the discovery of dark matter and dark energy has already had profound implications for our understanding of the universe. These mysterious components, which together make up most of the universe's mass and energy, force us to reconsider not just the structures of the cosmos, but the very nature of space and time itself. While the impact of dark matter and dark energy is minimal within our own solar system, their influence on interstellar travel and colonization could be far more significant. The discovery and study of these enigmatic forces may ultimately be key to unlocking the mysteries of deep space travel and the potential for humanity to expand beyond our solar system. However, when we consider the prospect of venturing beyond the familiar confines of our cosmic neighborhood, the forces that govern the universe become not just important, but pivotal. Dark matter, that invisible substance embedded within the halos of galaxies, might play a crucial role in shaping the trajectory of spacecraft and the distribution of vital resources within distant star systems. The very nature of this mysterious matter could significantly alter our calculations, potentially forcing us to rethink the very foundations of space navigation. In parallel, the elusive force known as dark energy, and which drives the acceleration of the universe's expansion, presents both formidable challenges and remarkable opportunities for humanity's long-term colonization efforts. As galaxies hurtle farther apart at an ever-increasing rate, the window for intergalactic travel gradually narrows, emphasizing the urgency for humanity to develop propulsion technologies that are not just more advanced, but more suited to the realities of an ever-expanding universe. This urgency might prompt the prioritization of finding habitable worlds within our cosmic vicinity, narrowing the scope of our exploration while increasing the complexity of our journey. The knowledge and mastery of dark matter and dark energy, however, could open the door to revolutionary technologies. Harnessing these forces might enable us to break free from the limits of current propulsion systems, unlocking entirely new ways to travel through space, produce energy, or even manipulate gravity itself. Such breakthroughs would not merely enhance our ability to reach distant stars, they could redefine the possibilities of space travel and make previously unreachable planets and star systems accessible in ways we've only dreamed of. The mysteries of the cosmos, once confined to the realm of science fiction, could become an undeniable part of our reality. If space were not the vacuum we understand it to be, the entire landscape of space exploration and industry would shift dramatically. The presence of matter, whether gases or particles, scattered throughout space would introduce a significant form of resistance, much like the drag created by air on Earth. This resistance would require us to develop propulsion systems of unimaginable power, ones that could overcome this new force and allow spacecraft to travel at the speeds necessary for interplanetary or interstellar journeys. Satellites and space stations, which currently drift freely in the vacuum, would face the constant drag of particles, necessitating constant course corrections and frequent replacements. The very lifespans of these orbital structures would be slashed, increasing both the financial and logistical burden of space operations. The satellite networks we rely on for global communications would be unable to maintain stable orbits, disrupting the critical services that have become integral to our daily lives. Interplanetary travel, as we currently envision it, would become almost impossible. The vast distances between planets and stars, which spacecraft now cross effortlessly, would become almost insurmountable obstacles. The additional fuel required to overcome this constant resistance would make even the most ambitious space missions economically prohibitive. Our understanding of the universe, too, would change fundamentally. Many of our astronomical observations rely on the unobstructed travel of light and electromagnetic waves through the vacuum. If space were filled with matter, the light from distant stars and galaxies would be blocked or scattered, limiting our ability to observe and study the farthest reaches of the universe. As we look toward the future of space exploration, a new and unprecedented array of economic opportunities awaits us. The vast, largely untapped resources scattered across asteroids and other celestial bodies offer a tantalizing promise of wealth. These objects, rich in precious metals like platinum, gold, and rare earth elements, could alleviate the looming scarcity of such materials on Earth, driving the next wave of technological innovation. Space mining has the potential to not only support the growing needs of humanity, but to change the very nature of industry as we know it. Space-based manufacturing could revolutionize production on Earth. The microgravity environment of space allows for the creation of purer materials, more perfect crystals, and alloys that simply cannot be produced under Earth's gravity. These innovations could bring about breakthroughs in fields like medicine, electronics, and materials science, pushing us into a new technological age. The rapid expansion of satellite services, driven by the demand for communication and Earth observation, could spark the growth of entirely new industries. Space-based communication systems could deliver global internet coverage, while satellites dedicated to weather forecasting could drastically improve our understanding of climate patterns, offering solutions to some of Earth's pressing environmental challenges. Moreover, the blossoming space tourism industry, once the preserve of the ultra-wealthy, may soon become a more accessible experience. As technology advances, the possibility of orbital hotels, lunar excursions, and space travel could evolve into entire economies centered around the exploration and commercialization of space. Meanwhile, the potential for space-based energy production remains a transformative possibility. Solar power satellites, positioned beyond Earth's atmosphere and uninterrupted by the planet's day-night cycle, could provide a constant, clean energy source, beaming solar power back to Earth. This innovation could play a key role in addressing the energy demands of an increasingly power-hungry world. The costs associated with space exploration and exploitation are set to evolve dramatically in the coming years. At first, these endeavors will likely remain prohibitively expensive due to the immense investment required for research, infrastructure, and development. However, as technology improves and efficiencies increase, we can expect these costs to decrease, making access to space more affordable. The development of reusable rockets, as seen with companies like SpaceX, has already led to a significant reduction in the cost of launching payloads into orbit. This trend is expected to continue, making space more accessible to a wider range of organizations, governments, and even private individuals. As we push further into space, the economic viability of mining asteroids for rare resources could offset some of the costs associated with exploration. As the capabilities for extracting valuable minerals from these cosmic bodies grow, the financial incentives for space ventures will become even greater, fostering an environment where space exploration could generate revenue, helping to fund future missions. However, new challenges will emerge as humanity expands deeper into space. Long-distance missions, whether to Mars or beyond, will require significant investments in life support systems, radiation shielding, and advanced propulsion technologies. While these technologies may be costly at first, their development will likely become more efficient over time as we gain experience and adapt to the unique challenges of space travel. As humanity increases its presence in space, new insurance and liability challenges will arise. Traditional insurance models are already being stretched thin by the novel risks and astronomical costs associated with space activities. One of the growing concerns is the rising risk of collisions in low Earth orbit, as the number of satellites and space debris steadily increases. The potential for damaging valuable assets or triggering cascading collisions in space is a very real risk. Insurance companies will have to develop new methods for pricing these risks, which could result in damages worth billions of dollars. Another pressing issue is the liability for damage caused by falling space debris. Should a satellite or spacecraft re-enter the Earth's atmosphere uncontrollably and cause harm on the ground, determining who is responsible for the damage, especially when multiple private entities or nations are involved, will become increasingly complex. For human missions, the need for insurance extends far beyond the spacecraft and equipment, encompassing the health and safety of astronauts themselves. This includes coverage for long-term health effects from extended space travel, which are still not fully understood. As space tourism emerges as a commercial industry, new insurance products will be necessary to protect both operators and participants, covering the unique risks inherent in personal space travel. Finally, as humanity ventures further into the depths of space, the question of property rights becomes increasingly complex. Traditional concepts of ownership and territorial claims do not fit easily into the cosmic realm. Under the current framework of international space law, governed by the Outer Space Treaty of 1967, no nation can claim sovereignty over celestial bodies. This prohibition creates significant challenges for future space exploration and colonization efforts. As nations and private entities push the boundaries of space, the question of who owns what and how we manage the resources we discover will shape the future of human activity beyond Earth. As humanity looks toward the future of space exploration, the growing interest in extracting and utilizing extraterrestrial resources is prompting a fundamental shift in how we think about space laws. Water ice on the moon and valuable minerals on asteroids are just the beginning of could be a vast new frontier for resource extraction. And with this, new legal frameworks are needed. For some nations and private companies, the concept of owning and exploiting space resources is an enticing prospect, one that could dramatically alter our understanding of property rights beyond Earth. One potential model being discussed is the granting of usage rights rather than full ownership of space resources. This would allow entities to tap into these resources, but without claiming actual territory in the traditional sense. This nuanced approach may provide a balance between exploration and preservation, ensuring that space remains accessible to all, while still enabling its resources to be used for commercial purposes. Alongside this, the issue of space property rights is also expanding into less tangible domains, such as orbital slots and radio frequencies. As the Earth's orbit fills with satellites, the need to manage these increasingly crowded spaces is becoming pressing. A system akin to leasing, where specific orbital slots are allocated to different entities, could help prevent chaos in space, similar to how radio frequencies are managed on Earth. As we push the boundaries of human presence in space, questions about land use and habitation rights will become more urgent, particularly as permanent bases are established on the Moon, Mars, or even distant moons of Jupiter and Saturn. This new phase of space exploration will demand a new breed of space law, one that balances the idea of space as the common heritage of humanity with the practical needs of those who will live and work in space. It is crucial that legal structures evolve to accommodate both the needs of space settlers and the burgeoning commercial enterprises that will drive economic activity in space. The way these laws are shaped in the coming years will have a profound effect on how humanity expands its reach into the cosmos. With this expansion, new markets for space resources will likely flourish. Asteroid mining, for example, presents the possibility of tapping into resources such as platinum, gold, and rare earth elements in quantities far surpassing what is available on Earth. These metals could be used in space-based manufacturing or brought back to Earth to fuel the growing demand for electronics and high-tech industries. Water, extracted from asteroids or lunar ice deposits, could become one of the most valuable commodities in space. Not only could it support life in extraterrestrial habitats, but it could also be broken down into hydrogen and oxygen, providing a source of rocket fuel. Additionally, water could be used as radiation shielding, protecting both spacecraft and future space settlers from harmful cosmic radiation, making deep space missions much more feasible and cost-effective. Meanwhile, solar power satellites represent another intriguing possibility for space-based resource use. By capturing the sun's energy in space, where there is no atmospheric interference, these satellites could beam clean, abundant electricity back to Earth. This could revolutionize the global energy market, offering a new, sustainable source of power. Helium-3, an isotope that is rare on Earth but abundant on the Moon, is another resource that could have profound implications for the future. This isotope could potentially be used as fuel for fusion reactors, offering a nearly limitless energy source if the technology to harness it is developed. As technology advances, space tourism is emerging as a new industry. With several companies already offering suborbital flights, the possibility of orbital hotels, lunar excursions, and even trips to Mars could soon be within reach. This growing market will require a new array of support services, including space transportation, life support systems, and an infrastructure to accommodate space tourists. The idea of people traveling to space, whether for leisure or business, may soon become a common reality, leading to a new era in both space exploration and commercial ventures. However, as humanity ventures deeper into space, there is a growing need to update and refine the international legal frameworks that govern space exploration. The current system, largely based on treaties formed during the 1960s and 70s, is increasingly outdated. It must evolve to address the complexities of modern space exploration, particularly when it comes to resource extraction. As more companies and nations begin to mine asteroids and other celestial bodies, clearer regulations will be necessary to define who has the right to extract resources and how profits should be shared. This will require a delicate balance between ensuring that space remains a common heritage for all and incentivizing private investment and exploration. Another pressing concern is the management of space traffic. With more satellites and increasing space debris orbiting Earth, it is crucial to establish international protocols to prevent collisions and ensure the sustainable use of space. These protocols could include guidelines for satellite design, deployment, and decommissioning, as well as measures to limit the creation of space debris. Additionally, the environmental impact of space exploration must be considered, as must the rights of future space settlers and the governance of potential off-world colonies. As humanity looks to establish permanent settlements beyond Earth, the legal frameworks that govern these colonies will need to ensure peaceful and equitable access to space for all. As we continue to push the boundaries of space exploration, some ideas that once seemed purely speculative are inching closer to becoming a reality. One such possibility is the development of wormholes, which could provide shortcuts through space-time, allowing for faster-than-light travel. While still highly theoretical, recent advancements in physics suggest that manipulating space-time might not be as far-fetched as once thought. Scientists are exploring ways to make wormholes a reality, potentially opening up new avenues for travel across the cosmos. This could one day allow us to reach distant stars and galaxies, forever changing our understanding of the universe. Another science fiction concept that is gaining traction is the idea of uploading human consciousness to computers. Advances in neuroscience and artificial intelligence are steadily bringing us closer to this possibility. By mapping the human brain and understanding its complex processes, scientists are unlocking the secrets of consciousness itself. In the future, it may become possible to transfer our minds to digital platforms, allowing us to live on in virtual worlds or even in the cloud. While this raises profound ethical and technical questions, the idea of uploading human consciousness may one day move from science fiction to science fact. The search for extraterrestrial life is also advancing rapidly, thanks to new technologies that allow us to explore distant planets and moons more effectively. Advanced telescopes and space probes are now capable of detecting biosignatures on exoplanets, and while we have not yet found definitive proof of alien life, the increasing number of exoplanets discovered around distant stars suggests that the likelihood of finding life beyond Earth is growing. This raises intriguing possibilities about the future of human space exploration. As the discovery of extraterrestrial life could radically reshape our understanding of the universe and our place within it. Lastly, the rapid development of artificial intelligence is bringing us closer to a future where machines play a central role in scientific discovery and technological innovation. While we are still far from creating sentient robots, AI systems are becoming increasingly sophisticated, capable of solving complex problems faster and more efficiently than humans. This progress raises fascinating questions about the relationship between humans and machines, particularly in fields like space exploration, where AI could be instrumental in managing resources, navigating spacecraft, and even conducting scientific experiments on distant planets. As we look toward the future of space exploration, one concept looms large: faster-than-light travel. This staple of science fiction presents one of the greatest challenges to our understanding of physics. According to Einstein's theory of special relativity, nothing can travel faster than the speed of light in a vacuum. This speed limit is not just a rule, but a fundamental aspect of how our universe operates. If faster-than-light travel were possible, it would require an enormous amount of energy, as an object's mass increases exponentially as it approaches the speed of light. In theory, it would take an infinite amount of energy to accelerate an object with mass to this speed, making it impossible to achieve. While faster-than-light travel remains a distant dream, advancements in physics may one day offer new insights into how we might overcome this barrier and unlock the secrets of the cosmos. However, some theoretical physicists have ventured into concepts that, although they seemed to belong more to the realm of science fiction than fact, are still explored in great depth. Among these are ideas like wormholes or the Aluia drive, which, in theory, could provide a way to travel faster than light by bending or warping the very fabric of space-time. These proposals, while mathematically intriguing, remain deeply speculative, riddled with numerous practical and theoretical obstacles. Yet, despite the uncertainty, the pursuit of faster-than-light travel continues to drive the imagination and intellectual curiosity of scientists and engineers alike. The question of whether such travel could one day be feasible, or how it might fundamentally alter our understanding of physics, continues to captivate minds, pushing the boundaries of our knowledge and fueling a never-ending quest for the unimaginable. Beyond Earth, in environments where the space gives way to more exotic settings, the possibilities for life form and evolution explode into a realm of endless imagination. In places with dense atmospheres, we might encounter alien creatures that navigate the thick, gaseous surroundings by floating or flying with the help of gas-filled bladders or intricate wing-like appendages. These beings could possess extraordinary sensory organs, finely tuned to pierce through the dense layers of their home planets, enabling them to navigate the oppressive atmospheres that might even be opaque to human vision. The diversity of life could be staggeringly different from anything we've encountered, adapted to thrive under harsh, unfamiliar conditions. In liquid environments, such as the hidden oceans beneath the icy crusts of moons like Europa, life might evolve in forms resembling Earth's deep-sea creatures. The dark, cold depths of these alien worlds could harbor bioluminescent organisms, creatures that use light not only for communication and attracting prey, but also as a means to confuse and ward off potential predators in a world where sunlight never penetrates. These organisms might display the ability to alter their shapes, flexing their bodies to withstand crushing pressures. In such realms, energy could be sourced not from the sun, but from the chemical reactions present in the water, using chemosynthesis in place of photosynthesis, much like some of Earth's extremophiles. On planets where gravity is stronger than Earth's, the forms of life would be constrained by the oppressive weight of their environments. To survive, these creatures could evolve to be shorter and stockier, with multiple limbs working together to distribute their weight evenly. Their bodies would likely be made from stronger yet lighter materials to support their heavy frames. In contrast, planets with low gravity would foster creatures that are tall and spindly, their elongated limbs and slender bodies a necessity to move efficiently in such an environment. The potential for alien life forms doesn't stop with just differences in morphology and behavior. As we push the limits of our imagination, we can even speculate about the chemical foundations of life itself. Could life exist based on elements other than carbon, such as silicon, forming the foundation of an entirely different biochemistry? These life forms might have crystalline structures, metallic components integrated into their biology, or entirely unique cellular structures that result in appearances and behaviors unlike anything on Earth. The vast possibilities for what alien life might look like, how it might think, and how it might behave are limited only by the fundamental laws of physics and chemistry. These laws, while restrictive in one sense, also allow for a staggering array of potential life forms, each adapted to the extreme environments of their worlds. When considering life in non-vacuum space, the reality of space combat would be drastically different from the thrilling close-quarters battles often depicted in science fiction. Gone would be the dramatic dogfights with ships darting through the void in a flurry of laser beams. Instead, space warfare would unfold across unimaginable distances, with engagements lasting not minutes, but potentially hours or even days. Space combat would rely heavily on long-range sensors, advanced targeting systems, and computational algorithms, as visual contact would be nearly impossible in the vast emptiness of space. Weapons that we are familiar with, such as lasers, would face significant limitations in space combat. Although directed energy weapons like lasers could still be used, their effectiveness would diminish with distance, as the vacuum of space allows for little to no medium through which they can travel efficiently. Kinetic weapons, such as sophisticated missiles or high-velocity projectiles, might prove more practical, as they could maintain lethal speeds and impact despite the absence of an atmosphere. In such a scenario, the concept of stealth would be paramount. Ships would need to minimize detectable emissions, from heat signatures to any other traceable signals that could give away their position. The absence of air resistance would profoundly change the physics of maneuvering during combat. Every action, whether firing a weapon or altering course, would cause a ship to shift its trajectory, requiring precise calculations and careful management of energy resources. The idea of thrust, as we understand it on Earth, would take on an entirely new meaning. Additionally, debris from destroyed vessels would become a significant hazard, potentially creating vast fields of shrapnel that could remain a threat long after the battle has ended. With the vast distances involved, communication between ships or with command centers could take minutes, hours, or even longer. The delay in transmissions would force commanders to act with little to no real-time feedback, relying on highly autonomous systems to make critical decisions on the fly. As our understanding of the cosmos deepens, science fiction writers are presented with an ever-expanding canvas, one that invites the exploration of ideas grounded in the latest discoveries in astrophysics and cosmology. One fascinating avenue could involve the multiverse, the notion of multiple parallel universes, each with its own set of physical laws. These stories could explore the consequences of minor variations in fundamental constants, where even small changes could create radically different versions of reality. What if the universe were slightly different in another dimension, and what would the beings there experience? Another captivating genre might be born from the study of dark energy and the accelerating expansion of the universe. This could inspire narratives set in a far future where galaxies, once part of a vast interconnected cosmic web, are now isolated islands, drifting further apart as the universe expands at an ever-increasing rate. These stories could revolve around civilizations struggling against the relentless isolation, racing to preserve knowledge and communication with other species before they are forever cut off from the rest of the cosmos. The search for extraterrestrial intelligence, SETI, could provide fertile ground for writers who wish to explore the implications of first contact. These scenarios might involve encounters with life forms so alien that they challenge our very understanding of intelligence and consciousness. Imagine beings that exist in higher dimensions, creatures that communicate in ways we cannot yet comprehend, pushing the boundaries of what it means to be alive or intelligent. These tales could delve into the philosophical, psychological, and social ramifications of making contact with such radically different forms of life. In all these possibilities, one thing is clear. The limits of our understanding are ever expanding, and as we reach further into the cosmos, so too does the realm of science fiction. The wonders of space, both real and imagined, will continue to inspire awe and curiosity, pushing us toward an unknown future where the line between science and fiction becomes ever more blurred. Advances in our understanding of quantum mechanics and the fundamental nature of reality could shape stories that challenge our deepest perceptions of existence. These tales might explore concepts such as consciousness being a core component of the universe itself, or the radical notion that reality, as we know it, is a form of cosmic simulation, carefully constructed and maintained. Such stories would push the boundaries of science fiction, blurring the lines between the physical world and the metaphysical realms that we have yet to fully comprehend. In this reimagined universe, the traditional space opera would need to undergo profound reinvention to align with our current understanding of the cosmos. Gone would be the days of faster-than-light travel, a trope that, in light of modern physics, now seems more fantastical than ever. No longer would our heroes zip through space at unimaginable speeds, effortlessly bypassing the laws of relativity. Instead, interstellar journeys would stretch across decades, centuries, or even millennia. Space travelers might rely on methods like cryogenic sleep, where they could enter stasis for long periods, or the use of generation ships, vast, self-sustaining vessels that would house multiple generations of explorers. These long, slow voyages would give rise to new kinds of drama, focusing not only on the scientific challenges, but also on the social, psychological, and emotional impacts of extended isolation. Alien civilizations, which have long been a cornerstone of space opera, would also be depicted in ways that radically depart from tradition. The familiar humanoid forms of extraterrestrial life would likely be replaced with beings whose biology and chemistry are as alien as the farthest reaches of the galaxy. These life forms might not even be carbon-based. Imagine, for instance, silicon-based life, or entities whose biochemistry operates on entirely different principles, beings so strange that our human minds would struggle to even fathom their existence. Communication with such beings would be an enormous challenge, not merely a matter of learning new languages, but one of understanding completely foreign methods of perception, thought, and interaction. The environments of these alien worlds would require an even more radical overhaul as the harsh realities of space come into sharper focus. Planets in our own solar system, Venus, Mars, or the moons of Jupiter, are already known to present extreme conditions such as crushing pressures, toxic atmospheres, and radiation levels that would render them completely inhospitable to humans. The space operas of tomorrow would grapple with these conditions, forcing heroes to survive on alien worlds where they must contend with dangers far beyond the threat of villainous alien forces. These are worlds that might demand cutting-edge technology and often personal sacrifice. In the realm of warfare, space opera battles would bear little resemblance to the familiar dogfights of old. Space combat would likely occur at vast, near-impossible distances, far beyond the limits of human vision. The traditional imagery of blazing starships and dramatic explosions would give way to a colder, more methodical form of conflict. Instead of flashy space battles, military operations might rely on automated systems, artificial intelligence, and sophisticated algorithms to outmaneuver opponents. The vast silence of space, combined with the emptiness between celestial bodies, would transform warfare into a quiet, dispassionate, and perhaps unsettlingly precise series of calculated moves. The human element of battle might be stripped away, leaving behind a conflict defined by technology, strategy, and the ever-present danger of being lost to the uncaring void of space. Yet, despite these sobering realities, the universe would be teeming with mysteries that could drive compelling narratives and mind-bending adventures. Writers would have the opportunity to explore the vast unknowns of space in ways that challenge both scientific understanding and the imagination. One such fascinating plot device could center on the manipulation of dark matter, an enigmatic substance that, though invisible and still largely misunderstood, makes up a significant portion of the universe's mass. Characters might discover how to harness dark matter, or even communicate through it, unlocking entirely new realms of possibility for interaction, exploration, and conflict. The manipulation of dark matter could open up portals to regions of the universe where the normal laws of physics break down, creating opportunities for dramatic discoveries and perilous challenges. Another compelling concept could involve the exploitation of exotic states of matter, such as quark-gluon plasma or Bose-Einstein condensates. These strange and unique forms of matter, which exist only under extreme conditions, could become the key to understanding alternate dimensions, or could serve as sources of nearly limitless power. The manipulation of these extraordinary substances could lead to narratives filled with discoveries, dangers, and the potential for catastrophic consequences. What might happen if such exotic matter fell into the wrong hands, or if an experiment went awry? These questions could form the backbone of high-stakes thrillers set in a future where science has stretched far beyond its current boundaries. Quantum entanglement, a phenomenon that allows particles to remain interconnected regardless of the distance between them, could also serve as the foundation for gripping cosmic narratives. Imagine a story where characters can manipulate quantum entanglement on a universal scale, enabling them to instantaneously affect distant parts of the universe. This could introduce all manner of unforeseen consequences, from unintended disruptions to entire star systems, to moral dilemmas about the extent of one's responsibility in a universe of interconnectedness. The implications of such power would stretch into questions of ethics, causality, and the very fabric of reality itself. Finally, the concept of programmable matter could offer fertile ground for new and exciting storytelling. Characters might encounter or even develop substances capable of reshaping themselves at will. These materials could shift from one form to another, adapting to different needs and environments, effectively blurring the lines between technology and biology. Such substances would offer infinite possibilities. Ships that could grow or change shape depending on their environment, or devices that could be reprogrammed on the fly. This idea could lead to thought-provoking narratives exploring the very nature of reality, the concept of identity, and the risks of unchecked scientific advancement. In such a world where matter itself can be manipulated like clay, what would be the cost of creating a universe so malleable? In this brave new world of space opera, the old tropes would be turned on their head. The stories might not be about light-speed travel, alien invasions, or epic battles across the stars. Instead, they would be about survival in a universe that refuses to conform to human expectations, where the true limits of science and understanding have only just begun to unfold. Here, the greatest challenges would not always be physical, but intellectual and moral as humanity grapples with its place in a universe that is far stranger and more mysterious than we ever could have imagined.